Hello, dear dreamer. Welcome back to this quiet corner of the internet, this gentle space where science meets serenity, where curiosity and rest fold into one another, like waves meeting shore. Perhaps your lights are dimmed, the day's noise has finally quieted, and the world outside taps its ancient rhythm against your window. Wherever you are in this wide world, whatever constellation might be visible above you right now, you're welcome here. Settle in. This is your moment. Your willingness to learn while letting go is a gift you give yourself. I'm talking about Mercury, the planet that's basically kissing the sun right now, the world that orbits so close to our star that it completes a full year in just 88 Earth days, the place where the daytime ground temperature regularly soars past 430 degrees Celsius. Mercury's ice is proof that the solar system is full of surprises, that reality is more creative than our assumptions, and that even the most extreme environments can hide pockets of the unexpected, if you just know where to look and understand the geometry. The volcanic surprise nobody saw coming. For a long time, really stretching from the Mariner 10 era in the 1970s, all the way through the early 2000s, the scientific consensus on Mercury was pretty straightforward. It's basically a dead moon that happens to orbit the sun instead of another planet. Just endless craters stacked on top of craters, layer upon layer upon layer, shaped by nothing but billions of years of relentless cosmic bombardment and absolutely nothing else. The thinking went like this. Mercury is small. It cooled down fast. Its interior froze solid early in its history, and from that point on it was just a passive target sitting in space, getting pummeled by every piece of debris that wandered through the inner solar system. Impact, crater, repeat. That was supposedly Mercury's entire geological story. Simple, straightforward, boring. Turns out we were completely, fundamentally wrong about that assumption. Mercury had a volcanic phase, not just a few scattered, isolated eruptions here and there that barely made a dent in the overall landscape. No, Mercury had a big, dramatic, planet-altering, geologically significant volcanic episode that reshaped huge portions of its surface. How huge? We're talking about smooth volcanic plains that cover millions of square kilometers, roughly 27% of the planet's entire surface area. That's an area comparable to the size of North America and Europe combined. These aren't minor features you have to squint to see. They're major geological provinces that fundamentally changed Mercury's appearance. For years after their discovery, the scientific debate raged. What exactly were these smooth plains? Were they pools of impact melt, rock that had been melted by the incredible energy of giant asteroid impacts, and then spread out across the surface in sheets, cooling back into solid rock? Or were they actual volcanic eruptions, real honest-to-goodness lava flows that came from deep inside Mercury's mantle, rose to the surface, and poured across the landscape like the basaltic lava flows we see on Earth, the Moon and Mars? The distinction matters enormously. Impact melt tells you about the violence of collisions. Volcanic lava tells you about the thermal state and chemical composition of a planet's interior. They're answering completely different questions about Mercury's history and evolution. As MESSENGER collected more and more data, mapping the entire planet in high resolution, measuring chemical compositions from orbit, and documenting the detailed relationships between different surface units, the evidence increasingly pointed toward volcanism, real eruptions, real lava, real magma rising from Mercury's mantle and flooding across the surface. How can we tell the difference? The details matter, and they tell a clear story. First, these smooth plains have flow fronts, subtle edges and margins where you can see that something fluid advanced across the landscape and then stopped and solidified. These aren't the circular or radial patterns you'd expect from impact melt spreading out from a central explosion. They're sinuous, winding margins that follow topography the way a liquid would, advancing into low areas and lapping up against high ground. Second, the plains embody older features, meaning they flow around and partially bury obstacles. You can see isolated hills and mountains of older, rougher terrain sticking up through the smooth plains like islands in a frozen sea. The plains clearly flowed around these obstacles, which is what lava does. Impact melt doesn't create that kind of selective burial pattern. Third, and perhaps most importantly, their chemical composition is different from the surrounding highlands. They're not just melted and resolidified versions of whatever crust happened to be there. They have distinct elemental abundances, different ratios of key elements like iron, magnesium, aluminum, and silicon, pointing to material that came from depth, from Mercury's mantle, bringing its own unique chemical fingerprint to the surface. That's the smoking gun for volcanism. When you bring up fresh material from the mantle, it has a different composition than remelted crust. Chemistry doesn't lie. The biggest and most dramatic example of volcanic resurfacing is inside the Caloris Basin, that absolutely monstrous impact crater we talked about earlier, the one that's about 1,550 kilometers across, bigger than the state of Texas, one of the largest impact structures in the entire solar system. After the catastrophic impact that excavated Caloris, after the ground stopped shaking and the ejected debris stopped falling from the sky, after things settled down into an uneasy post-apocalyptic calm, something interesting happened. Lava welled up from below and began flooding portions of the basin floor. You can still see the evidence today. Large swaths of Caloris's interior are paved with smooth plains that have a distinctly different color and texture in calibrated images compared to the shattered, broken, impact-processed highlands that surround the basin rim. These plains clearly formed after the impact because they bury parts of the impact structure. They fill in low areas. They lap up against the terraced inner walls of the basin. They're younger than the basin itself, which means they're volcanic. Why would lava preferentially erupt into impact basins? Actually, that makes perfect sense from a geological perspective. A giant impact doesn't just excavate a hole, it fractures and weakens the crust for hundreds of kilometers around the impact site. It creates a complex system of faults and cracks that extend deep into the lithosphere, and if there's any magma lurking in the mantle below, those impact-created fractures provide easy pathways for that magma to reach the surface. It's like the impact drilled a series of wells into Mercury's magma reservoirs, and the magma gladly accepted the invitation to come up and visit the surface. But Mercury's volcanism wasn't confined to big impact basins. As Messenger mapped the planet in detail, volcanic plains turned up everywhere, in smaller craters, in low-lying regions between older highlands, spread across ancient terrain, filling in low spots and creating vast, relatively smooth surfaces where before there was nothing but cratered, battered, rough ground. And it wasn't all just gentle, effusive lava flows quietly oozing across the surface. Mercury also experienced explosive volcanism, which is frankly kind of amazing on a planet with essentially no atmosphere. Scattered around Mercury's surface are volcanic vents, identifiable by their shallow, rimless depressions surrounded by distinctive halos of material with unusual colors and reflectance properties. These deposits often have a reddish or orange tint in false color images, making them stand out dramatically against the grayer surrounding terrain. These are the sites of explosive volcanic eruptions, places where gas-charged magma burst violently through the surface and sprayed volcanic glass, ash, and pyroclastic debris across the surrounding landscape, creating these distinctive aprons of material around the source vents. Now you might be thinking, wait, explosive eruptions on an airless planet. How does that work? Don't you need atmospheric pressure or water vapor to drive explosive volcanism? Great question, and the answer reveals something important about Mercury's interior chemistry. On Earth, explosive volcanism is often driven by water dissolved in the magma, As magma rises toward the surface and pressure decreases, that dissolved water comes out of solution, creating bubbles. Those bubbles expand rapidly, and if there's enough gas, they can literally tear the magma apart into fragments, creating explosive eruptions that spray ash and pumice across the landscape. On Mercury, the volatiles driving explosive eruptions aren't water, at least not primarily. Mercury formed in a region of the solar system where water was scarce, but other volatiles were present: sulfur compounds, carbon dioxide, and other gases that could dissolve in magma at high pressures deep underground. Even without atmospheric pressure at the surface, those volatiles can still expand dramatically as magma rises and pressure drops. The transition from high pressure at depth to near vacuum at the surface is so extreme that any dissolved gases will explosively exsolve, fragmenting the magma and launching pyroclastic debris on ballistic trajectories. Without an atmosphere to slow them down, those fragments travel farther and deposit in characteristic patterns that tell us about the violence and volume of the eruptions. The brightest, most distinctive pyroclastic deposits on Mercury span tens of kilometers across, suggesting substantial explosive events that ejected large volumes of material. But here's where Mercury's volcanism gets chemically weird and scientifically fascinating. The lava that built Mercury's smooth plains wasn't like typical Earth basalt. It was strange stuff. It had unusual chemistry that tells us something profound about Mercury's interior. Specifically, Mercury's volcanic rocks are unusually low in iron for volcanic materials. On Earth and the Moon and Mars, volcanic basalts are typically rich in iron, which is why they're dark and dense. But Mercury's lavas are poorer in iron and relatively richer in elements like magnesium and sulfur. That chemistry points to a very reducing environment during formation and melting, meaning an environment where oxygen was scarce. In oxygen-poor conditions, iron preferentially bonds with sulfur rather than oxidizing, and sulfides rather than oxides dominate the mineralogy. Mercury's volcanic chemistry is telling us that its interior formed and evolved under very different chemical conditions than Earth's interior. This makes perfect sense, given where Mercury formed, close to the Sun, in the hottest part of the early solar nebula. Oxygen was less available to bond with other elements. Metals and sulfur like to pair up instead. Mercury's entire interior apparently formed under those reducing conditions, and when parts of the mantle melted billions of years later and erupted onto the surface, the resulting lava carried that unusual reducing chemical signature. The volcanic era on Mercury eventually wound down and sputtered out. As Mercury's interior continued cooling over billions of years, as the mantle lost its remaining stored heat, as the temperature and pressure conditions needed to generate partial melting became harder and harder to achieve, the rate of volcanism decreased. The pathways for magma to reach the surface gradually froze shut, plugged by solidifying rock. Volcanic activity became sporadic, then rare, then ceased entirely. Mercury's last volcanic eruptions probably happened somewhere between 3 and 4 billion years ago. Since then, volcanism has been silent. The volcanic plains that formed during Mercury's active era are now just part of the ancient landscape, modified only by the steady rain of impacts that continues to this day. But those ancient lava flows are still there, perfectly preserved in many places. On Earth, volcanic plains get weathered by rain and wind, eroded by rivers, buried by sediments, and eventually recycled by plate tectonics, all within a few 100 million years at most. On Mercury, with no atmosphere, no water, no tectonic recycling, those billion-year-old lava flows look almost as fresh today as they did when they first solidified. That preservation is a scientific gift. It means we can study Mercury's volcanic history in detail, measuring the chemistry of ancient eruptions, mapping the extent of long-dead lava flows, and reconstructing the thermal evolution of Mercury's interior based on when and where volcanism occurred. and that history is written clearly across the surface. The smooth plains tell us that Mercury was volcanically active for a substantial period, probably from shortly after formation through the first billion years or so of its existence. The explosive deposits tell us that Mercury's magmas contained significant amounts of volatile elements, contradicting the old idea that Mercury was completely stripped of volatiles during formation. The unusual chemistry tells us about the reducing conditions in Mercury's interior, and the eventual cessation of volcanism tells us about the planet's cooling history and the thickening of its rigid lithosphere. From all of this, we can reconstruct a story: young Mercury still hot from formation, with a partially molten mantle capable of generating magma. Giant impacts fracture the crust and provide pathways. Lava rises and floods across the surface, filling basins and low-lying areas. Some eruptions are gentle and effusive, others are explosive and violent. For hundreds of millions of years, Mercury is volcanically active, resurfacing large fractions of its exterior. Then gradually, cooling takes its toll. The mantle solidifies, the lithosphere thickens. Magma generation becomes Mercury. The paradox planet full extended script. Here's something that'll absolutely blow your mind, and I promise this isn't clickbait. There's ice on the hottest planet in our solar system. Real, actual water ice. Frozen solid, and it's been sitting there, completely undisturbed, for millions of years. Wait, what? How does that even make sense? How is that physically possible? I'm talking about Mercury, the planet that's basically kissing the sun right now, the world that orbits so close to our star that it completes a full year in just 88 Earth days, the place where the daytime ground temperature regularly soars past 430 degrees Celsius. That's hot enough to melt lead, like it's butter on a summer sidewalk, hot enough to melt zinc, tin, and even some types of bronze. Hot enough that if you left a spacecraft sitting on the equator at noon, its metal components would start to soften and deform. And yet, hidden deep in the shadows of Mercury's polar craters, tucked away in places where sunlight has not touched the ground for millions of years, there are frozen lakes of water ice that have been sitting there, completely stable and undisturbed since before humans existed on Earth. And that's not even the weirdest thing about this planet. Not even close. In fact, that's just the opening act. See, Mercury is the absolute cosmic embodiment of expect the unexpected. It's a planet that seems to delight in breaking every rule we try to impose on it. It's absolutely tiny, the smallest planet in our solar system, barely larger than our moon, and yet it's mostly made of dense iron and nickel. It races around the sun faster than any other planet, completing its orbit in less than 3 Earth months. But a single day on its surface, measured from one sunrise to the next, lasts longer than half an Earth year. By every reasonable scientific model, Mercury should be geologically dead. Its interior should have frozen solid billions of years ago. It should be a cold, inert ball of rock with nothing happening beneath its battered surface. But it's not. Deep inside its core, there's still liquid metal churning and flowing, generating a weak but unmistakable magnetic field that wraps around the entire planet like an invisible protective bubble. Stick around, because by the end of this video, you're going to see exactly why this little rock, this often overlooked member of our solar system family, is genuinely one of the strangest, most fascinating, most paradoxical, and most scientifically valuable places we've discovered anywhere in our cosmic neighborhood. Trust me, Mercury has more than earned its reputation as the paradox planet, the impossible magnetic field that shouldn't exist. Alright, here's where Mercury really starts breaking the rules of planetary science and showing off just how weird it truly is. In planetary geology and geophysics, there's a pretty straightforward, well-established rule of thumb that scientists have relied on for decades. Small planets are supposed to be dead inside, not resting, not dormant. Dead, completely inactive, geologically inert. The logic is simple and based on solid physics. Small planets have a high surface area relative to their volume. That's just geometry. And that high surface to volume ratio means they radiate heat into space very efficiently. They cool down fast, losing their internal heat within the first billion years or so of their existence. As a planet cools, its interior solidifies. The molten rock in the mantle freezes into static, unmoving stone. The metallic core, if it has one, crystallizes into a solid lump, and once everything is frozen solid, that's essentially it. Game over. The planet becomes geologically dead. No more volcanic eruptions because there's no more molten rock to erupt. No more tectonic activity because there's no more heat to drive it. And critically for our story, no more magnetic field because magnetic fields require moving, electrically conductive fluids, and you can't have moving fluids if everything is frozen. This fate has befallen most small bodies in our solar system. The Moon, slightly smaller than Mercury, is geologically dead. It has no magnetic field today, though it once did billions of years ago. Mars, which is larger than Mercury, is mostly geologically dead, with only hints of recent volcanic activity and no global magnetic field. Small moons like Enceladus are exceptions, but they're kept warm by tidal heating from their parent planets. Mercury doesn't have that excuse. It orbits the Sun, not another planet. By every reasonable expectation, by every model scientists had built, Mercury should have frozen solid billions of years ago, probably within its first billion years of existence. It should be a cold, quiet, inert ball of rock and metal with absolutely no magnetic field, no geological activity, and nothing interesting happening in its interior. Mercury apparently didn't get that memo, or it read the memo, understood it perfectly, and decided to ignore it anyway. When NASA's Mariner 10 spacecraft made its first flyby of Mercury in March 1974, scientists were excited, but their expectations were modest. They expected to see a heavily cratered surface, which they got. They expected to find an airless world, which they got. And they expected to find no magnetic field whatsoever, just like the Moon. Instead, as Mariner 10 swept past Mercury on the day side and then arced through the planet's shadow on the night side, something completely unexpected happened. The spacecraft's magnetometers, instruments designed to measure magnetic fields, started registering readings that looked suspiciously, unmistakably, like a planetary magnetic field. Not just a random patch of magnetized crustal rocks here and there, like we see scattered across the Moon and Mars, where ancient magnetic minerals have retained a memory of long-dead magnetic fields. No, this was an actual, organized, coherent dipole magnetic field wrapping around the entire planet like an invisible protective bubble carved out of the solar wind. The mission scientists were genuinely shocked. Some were skeptical at first. Could it be an instrumental error? Could the solar wind be doing something weird that was confusing the readings? Could there be some other explanation that didn't require Mercury to have an active magnetic field? But the data was clear. The signature was unmistakable. Mercury had a global magnetic field. The planet was generating its own magnetic bubble, its own miniature magnetosphere, just like Earth does, albeit on a much smaller scale. Sure, Mercury's magnetic field is weak. Very weak. It's only about 1% of the strength of Earth's magnetic field at the surface. It's a whisper compared to our planet's robust magnetic roar. If Earth's magnetic field is a symphony orchestra playing fortissimo, Mercury's is a single violin playing pianissimo in a practice room. But it was there. It was real. It was organized. It had a dipole structure, meaning it had a north magnetic pole and a south magnetic pole, just like a bar magnet, and it absolutely, categorically should not have been there. This was one of the biggest surprises of the entire Mariner 10 mission, and it immediately raised a huge question: how? To generate a magnetic field through what's called a dynamo process, you need three very specific conditions to be met simultaneously, and all three are requirements, not options. First, you need a liquid, electrically conductive material somewhere inside the planet. For rocky planets, this usually means molten iron and nickel in the core. Pure rock won't work because molten rock is a poor electrical conductor. You need metal, liquid metal, capable of carrying electrical currents. Second, that liquid metal absolutely has to be moving in complex turbulent, ideally turbulent patterns. Still, unmoving liquid won't generate a magnetic field no matter how conductive it is. You need motion, circulation, convection, stirring. You need the liquid to flow and swirl and create moving loops of electrically conducting material. And third, you need an energy source to sustain that motion over geological timescales, meaning billions of years. Liquids don't just sit there and swirl on their own forever. Something has to drive the motion. Usually, this is heat escaping from the core, creating convection currents as hot material rises and cool material sinks. Or it can be compositional convection, where light materials are released from crystallizing regions and rise buoyantly through denser liquid. Mercury is tiny. It's smaller than Ganymede and Titan, moons that orbit other planets. It has a radius of only about 2,440 kilometers, making it barely larger than our moon. By all rights, by every simple thermal model scientists could construct, Mercury should have cooled down and frozen completely solid billions of years ago, probably within the first billion years after it formed. A frozen core can't generate a magnetic field. No liquid, no motion, no dynamo. It should have been an open and shut case. But it wasn't. Against all reasonable expectations, Mercury's core hasn't completely frozen, and that raises an obvious follow-up question. Why not? What's keeping Mercury's core at least partially liquid after more than 4.5 billion years? The answer, and this is one of my favorite discoveries in planetary science, involves chemistry coming to the rescue. Turns out, and this wasn't confirmed until detailed measurements by the Messenger spacecraft, decades after Mariner 10, Mercury's core isn't pure iron and nickel. It's alloyed with lighter elements, particularly sulfur. Good old sulfur, the element that gives rotten eggs their distinctive smell, the element that forms yellow deposits around volcanic vents. That same sulfur is mixed into Mercury's metallic core. Why does that matter? Because of a principle called freezing point depression. When you dissolve something into a liquid, it lowers the freezing point. This is why we put salt on icy roads in winter. Pure water freezes at 0 degrees Celsius, but salty water can stay liquid well below that temperature. It's why the ocean doesn't freeze solid even at the poles. The dissolved salt lowers the freezing point. The same principle applies to Mercury's core, but instead of salt dissolved in water, we have sulfur dissolved in iron. When sulfur mixes with molten iron in the right proportions, it dramatically lowers the melting point of the metal alloy. Pure iron melts at about 1,538 degrees Celsius. But an iron-sulfur alloy can remain liquid at significantly lower temperatures, potentially several hundred degrees cooler. That difference is absolutely crucial. It means Mercury's core can stay partially liquid at temperatures where pure iron would have completely solidified ages ago. The sulfur acts like a planetary antifreeze, keeping at least part of the core molten when it otherwise would have frozen. But there's more to the story. Having liquid metal isn't enough. You also need that liquid to be moving, and you need an energy source to drive the motion. Here's where Mercury's structure becomes important. Based on precise measurements of how the planet wobbles as it orbits the Sun, how it responds to the Sun's gravitational pull, and how its gravity field varies across its surface. Scientists have been able to construct a detailed model of Mercury's interior structure. The current best understanding is this: Mercury has a solid inner core at its very center, made of crystallized iron-nickel alloy. Surrounding that solid inner core is a liquid outer core, probably iron alloyed with sulfur, and possibly other light elements like silicon or oxygen. And then above that, there might be a thin but dense layer of iron sulfide, a compound of iron and sulfur, sitting right at the boundary between the metallic core and the rocky mantle. This layered structure is absolutely crucial for understanding how Mercury's dynamo works. As Mercury's interior gradually cools over billions of years, the solid inner core grows. It crystallizes from the inside out, like ice forming on a pond, but in slow motion over geological time. And as the inner core grows, as pure iron and nickel crystallize and join the solid inner core, they preferentially leave behind impurities in the remaining liquid. Specifically, they leave behind sulfur and other light elements. Those sulfur-enriched fluids are less dense than the surrounding liquid iron. They're buoyant, and buoyancy in a gravitational field means motion. The sulfur-rich liquid rises upward through the liquid outer core, while iron-rich liquid sinks downward to replace it. This creates convection currents, churning circulation patterns, continuous motion driven by compositional differences. That motion, that stirring of electrically conductive liquid metal, is exactly what you need for a dynamo. As the liquid moves through existing magnetic field lines, it generates electrical currents. Those electrical currents create new magnetic fields, and through a beautifully complex feedback process involving induction and amplification, those magnetic fields organize themselves and sustain themselves into the stable, coherent dipole field we observe today. It's like Mercury has a tiny but incredibly stubborn, incredibly determined heart deep inside that absolutely refuses to stop beating, no matter how small the planet is, no matter how old it gets. 4.5 billion years after formation, when by all rights it should have gone quiet ages ago, Mercury's metallic heart is still churning, still generating its magnetic pulse. But wait. There's one more delicious twist to this story, one more layer of weirdness. Mercury's magnetic field isn't even properly centered. It's lopsided, its offside significantly toward the planet's north, shifted by about 480 kilometers northward from Mercury's center. That might not sound like much, but for a planet with a radius of only 2,440 kilometers, that's nearly 20% of the way from center to surface. It's a substantial offset. What this means in practice is that the magnetic field strength is notably different in the northern hemisphere compared to the southern hemisphere. The north has a stronger field. The south has a weaker field. It's like someone installed the planetary magnet off-center, tilted and shifted toward one pole. Why? What causes this asymmetry? Scientists think it has to do with how heat is escaping from different parts of the core. Imagine the boundary between Mercury's metallic core and its rocky mantle. That boundary isn't uniform. The mantle isn't the same thickness everywhere. It's probably thicker in some regions and thinner in others, perhaps as a result of ancient giant impacts or just random variations in how the planet assembled. Where the mantle is thicker, it acts as better insulation, slowing down heat loss from the core beneath. Where the mantle is thinner, heat can escape more easily. This creates an asymmetric pattern of cooling. The dynamo responds to this asymmetry. In regions where cooling is more vigorous, convection in the liquid core is stronger. In regions where cooling is sluggish, convection is weaker. The result is a magnetic field that's stronger in some areas than others, and in Mercury's case, that manifests as a significant north-south asymmetry. There might also be a layer of stably stratified fluid somewhere in the outer core, Perhaps that dense iron sulfide layer at the core mantle boundary that suppresses convection more effectively in the southern hemisphere than in the north. The details are still being worked out, but the basic idea is clear. Mercury's dynamo is asymmetric because its thermal and compositional structure is asymmetric. Either way, Mercury is proving something really important, something that challenges our simple models of planetary evolution. Size is not destiny. When it comes to magnetic fields and geological activity, what matters is composition, internal structure, and the specific details of how heat escapes. Get those factors right, tune them just so, and even a planetary peanut, even the smallest planet in the solar system, can keep its internal engine running for billions of years. There's something almost inspiring about Mercury's magnetic field. This tiny world, barely larger than our moon, orbiting in one of the harshest environments in the solar system, constantly battered by intense solar radiation and the relentless solar wind, has maintained its magnetic heartbeat for over 4 billion years. It's a testament to the fact that even small voices can persist, that even modest systems can maintain their complexity against tremendous odds. The planet that literally shrank. While we're talking about Mercury's bizarre interior and what it's been doing over the past 4.5 billion years, let's discuss something that's written all over the planet's surface in spectacular fashion. What happens when a planet literally gets cold feet and physically shrinks? As Mercury's enormous iron core has been cooling over billions of years, steadily losing heat to the cold vacuum of space, it has been contracting. This isn't a metaphor. This isn't figurative language. The core is literally physically getting smaller. Metal does that when it cools. It contracts, taking up less volume. It's a basic property of matter. And when your core, which remember accounts for about 85% of the planet's radius and 70% of its mass, starts drawing inward, shrinking by multiple kilometers, your outer rocky shell has to adjust somehow. The mantle and crust that surround the core can't just float there unchanged while the interior pulls away beneath them. But here's the fundamental problem. Rock doesn't stretch, at least not on planetary scales, not in any meaningful way. Rock is strong in tension. Try to pull it apart and it will fracture and break rather than deform elastically. The crust can't simply shrink smoothly and uniformly along with the contracting core. It can't thin out and maintain a snug fit around the shrinking interior the way a deflating balloon maintains contact with the air inside. Instead, the only option available to the planet, the only way the rigid outer shell can accommodate a smaller interior, is for the crust to buckle, to fold, to break, and to thrust. One piece of crust has to climb up and over another piece, taking up the slack, fitting the smaller circumference by crumpling up like wrapping paper on a deflating balloon. The result is one of Mercury's most distinctive and spectacular geological features, giant cliff faces called lobate scarps. And when I say giant, when I say spectacular, I'm not exaggerating for effect. These are genuinely enormous geological structures. We're talking about thrust faults, compressional features that stretch for hundreds of kilometers across the landscape. Some of them extend for 500 kilometers or more, distances comparable to driving from Los Angeles to San Francisco or from London to Edinburgh. And they're tall, really tall. These scarps rise anywhere from a few hundred meters to more than a kilometer in height. That's taller than the tallest skyscraper on Earth. Imagine standing at the base of one of these cliffs, looking up at a wall of ancient rock that rises hundreds of meters vertically above you, extending to your left and right as far as you can see, curving away over the horizon. These lobate scarps cut indiscriminately across everything in their path. They slice clean through ancient, heavily cratered terrain that dates back billions of years. They dissect once smooth volcanic plains that were laid down later in Mercury's history. They offset younger impact craters, cutting through the circular rims and making neat chords out of what were once complete circles. They don't care what came before. They're writing their own story across Mercury's surface, a story of global contraction written in stone. Each lobate scarp is a thrust fault, a place where compression in the crust has caused one massive block of Mercury's rigid outer shell to ride up and over another block. The geometry is characteristic. One side of the fault, called the hanging wall, has been pushed up and over the other side, called the footwall, creating a step in the landscape. The hanging wall forms a rounded, gentle back slope. The footwall is exposed as a steep cliff face, the scarp itself, and at the base of the scarp, you often find a wedge of broken, jumbled rock that's collapsed and tumbled down from above. Picture a landscape where the ground itself has permanent, planet-scale wrinkles. Long, curved escarpments that cast sharp, dramatic shadows across the plains in the low-angle light of Mercury's prolonged sunrises and sunsets. Places where you could walk for weeks in Mercury time, which remember is much longer than Earth time, and still be following the same cliff, the same continuous fault line. Mercury has shrunk by approximately 7 kilometers in radius since its outer crust first solidified early in the planet's history. Let me repeat that with emphasis. The planet is 14 kilometers narrower in diameter today than it was billions of years ago. It has literally gotten smaller. Now, 7 kilometers might not sound like much when you're talking about a planet that's over 2,400 kilometers in radius. Right, that's less than 0.3% shrinkage. But when you're trying to fit a completely rigid, brittle shell, a shell that cannot stretch or compress elastically, around a sphere that's getting smaller, even that seemingly modest amount of shrinkage is more than enough to crumple and fold the entire surface into a complex maze of faults, cliffs, and ridges. To put it another way, if you could somehow measure the total horizontal distance around Mercury's equator today, and then add up all the horizontal shortening that's been accommodated by all the thrust faults and lobate scarps, you'd find that Mercury's crust has effectively shortened by about 14 kilometers of circumference. The crust has been squeezed, compressed, forced to take up less space on a smaller sphere. And here's something that really caught the attention of planetary geologists when they started mapping Mercury in detail. These lobate scarps don't just cut through ancient terrain. Many of them also cut across relatively young features. They slice through smooth volcanic plains that formed much later in Mercury's history, potentially only 3 to 4 billion years ago, rather than 4.5 billion years ago. They offset impact craters that are relatively fresh in geological terms, craters that still have sharp rims and bright rays. What this tells us is profound. Mercury wasn't just shrinking during its early history. During the first few 100 million years after it formed, it was still actively contracting relatively recently in geological terms, and it might even still be contracting today, albeit at an incredibly slow rate. This isn't just ancient history written in stone and forgotten. The planet is still settling, still very slowly adjusting to its cooling interior, still writing new chapters in its autobiography through these faults that continue to grow, albeit at rates so slow that you'd need to watch for thousands or millions of years to see measurable change. Some of these lobate scarps have been caught in the act, so to speak, of offsetting relatively young impact craters. You can see where a crater formed first, creating a nice circular rim. Then later, after the crater was already there, a scarp cut directly through it, lifting one half of the crater rim higher than the other half, offsetting the circle and turning it into a distinctive shape that immediately tells a story: impact first, then compression, then more slow adjustment. It's like watching tectonic activity in the ultimate slow motion, where each frame of the movie represents thousands or millions of years, but the story is undeniably still unfolding. When spacecraft like Messenger mapped Mercury's surface in high resolution, measuring the elevations precisely with laser altimeters, and imaging the scarps under different sun angles to bring out their relief, geologists were able to do something really clever. They could measure how much vertical offset each scarp had created, and they could measure approximately how much horizontal shortening had occurred. Add up all those measurements across the entire planet, and you get an estimate of Mercury's total global contraction. The numbers consistently point to about 7 kilometers of radius reduction, which translates to roughly 14 kilometers of crustal shortening around the equator. That's the smoking gun, the quantitative evidence that Mercury's enormous core has been cooling and shrinking throughout the planet's history. Compare this to other terrestrial planets, and the difference is striking. The Moon also has lobate scarps, evidence that it too has been shrinking as its interior cools, but the Moon's scarps are generally smaller and less extensive than Mercury's. The Moon has contracted by maybe 100 to 200 meters in radius, a much more modest amount. Earth doesn't show global contraction at all because our planet has plate tectonics and a vigorously convecting mantle that recycles the crust and accommodates internal changes in completely different ways. Mars might have experienced some early contraction, but again, nothing on the scale of Mercury. Mercury is the shrinkage champion of the terrestrial planets, and it wears that title in the form of spectacular planet-girdling cliffs that would dwarf anything on Earth. There's something almost poignant about these scarps. They're Mercury's wrinkles, the lines that come with age, the physical manifestation of billions of years of slow cooling. Every lobate scarp is a memory of heat lost, a record of Mercury's enormous metallic heart gradually, imperceptibly drawing inward as it radiates its warmth into the cold darkness of space. And those wrinkles are beautiful in their own stark way, under the low sun angles of Mercury's prolonged dawns and dusks. When shadows stretch for kilometers and every small topographic feature casts a long, sharp shadow, the lobate scarps create dramatic patterns of light and dark across the landscape. The steep cliff faces are in deep shadow, while the back slopes catch the light. The wrinkle ridges and subsidiary folds create complex textures. The whole surface looks sculpted, carved, three-dimensional in a way that flat planes never achieve. If you could somehow stand on Mercury's surface, perhaps inside a heavily shielded habitat at the base of one of these great scarps, you'd see a cliff rising above you, its face marked by the scars of ancient and recent impacts, its shadow a sharp line on the ground. You could follow that cliff for weeks of Mercury time, watching it curve across the landscape, watching it cut through crater after crater, watching the shadows shift as the sun makes its slow, patient journey across the star-filled black sky. These are not just geological features. They're a biography written in compression. They're the story of a planet that refused to cool quietly, that had so much metal inside it, had to reshape its entire surface to accommodate the consequences. They're proof that even in the absence of plate tectonics, even on a world with no atmosphere and no oceans and no biology, geology still happens, change still occurs. The planet is still alive in its own way, still responding to forces deep within, still carving its story into the rock for anyone patient enough to read it. Ice in hell. The polar paradox. All right, we've finally arrived at what is perhaps Mercury's single most delightful, most counterintuitive, most seemingly impossible feature. Ice. Real, actual, frozen water ice. On Mercury, the planet where daytime surface temperatures regularly exceed 430 degrees Celsius, the planet closest to the sun in our entire solar system. This is the kind of discovery that makes you fall in love with science, because it's so unexpected, so apparently contradictory, and yet so elegantly explained once you understand the geometry and physics involved. Let me explain exactly how this seemingly impossible situation actually works, because when you really dig into it, it's not just possible, it's almost inevitable given the right conditions, and Mercury has exactly the right conditions. It all starts with Mercury's axial tilt, or more accurately, its lack thereof. Earth's rotational axis is tilted about 23.5 degrees relative to the plane of its orbit around the Sun. That tilt is responsible for our seasons. When the northern hemisphere is tilted toward the Sun, we get summer because sunlight hits us more directly. When we're tilted away, we get winter. The Sun's angle in the sky changes dramatically throughout the year. In summer, the Sun climbs high overhead at noon. In winter, it stays low on the horizon. Mercury's rotational axis, by contrast, is tilted by only about 0.034 degrees. That's not a typo. 0.034 degrees. It's essentially upright, standing almost perfectly perpendicular to its orbital plane. For all practical purposes, Mercury doesn't have any axial tilt at all. What does that mean for how sunlight hits Mercury? It means the Sun never climbs high in the sky at the poles. Near Mercury's equator, the Sun gets very high, passing almost directly overhead during the long Mercurian day. But as you move toward the poles, the Sun's maximum elevation gets lower and lower. At the poles themselves, the Sun just perpetually skims along the horizon, circling around the landscape without ever rising more than a fraction of a degree above the horizon. Now imagine you're standing inside a deep crater near one of Mercury's poles. The crater walls rise high around you, maybe a kilometer or two tall. The Sun is circling the horizon, as it always does near the poles, but it never gets high enough to shine over the rim of the crater. The crater walls block the sunlight completely. You are standing on the floor of a crater that never sees the Sun. Not during Mercury's long day, not during any season, because Mercury doesn't really have seasons. Not ever, not in billions of years, because the geometry is stable. The Sun will never climb over that rim. These are called permanently shadowed regions, and they exist in scattered locations within deep craters at both Mercury's north and south poles, and they are cold. Not just cold by human comfort standards, but cold by any standard. Colder than Antarctica in the dead of winter, colder than the surface of Pluto in some cases. We're talking about temperatures that plunge to -200 degrees Celsius, or even lower. At those incredibly extreme temperatures, water ice is not just stable, it's effectively permanent. A water molecule that finds its way into one of these freezers will stay there for millions of years, potentially billions of years, until something physically excavates it, or until Mercury's orbital or rotational characteristics change significantly. But where does the water come from in the first place? How does water get to Mercury, the hottest planet in the solar system? The answer is both simple and beautiful. Delivery from space. Comets are essentially dirty snowballs, chunks of ice mixed with rock and organic compounds, left over from the formation of the solar system. They form in the cold outer reaches beyond Neptune's orbit, and sometimes their orbits get perturbed, sending them plunging into the inner solar system. Some of them hit planets, some of them hit Mercury. When a comet strikes Mercury at hypervelocity, typically tens of kilometers per second, most of the ice vaporizes instantly on impact. The kinetic energy of the collision converts to heat, and water ice flashes into steam. But here's the thing, Mercury has almost no atmosphere. That water vapor doesn't get carried away by winds or trapped in clouds. It just disperses across the surface as individual molecules following ballistic trajectories. On a planet with a thick atmosphere, those water molecules would eventually rain back down or get blown around. But Mercury has essentially no atmosphere, just that incredibly thin exosphere we talked about earlier. Water molecules released by an impact just hop across the surface. They make these long ballistic arcs, like extremely slow bullets, bouncing from place to place under Mercury's low gravity. Most of these water molecules eventually gain enough energy, through random thermal kicks or through interactions with sunlight and the solar wind, to escape Mercury's weak gravitational pull entirely. They're lost to space forever, contributing to the general background of hydrogen and oxygen atoms scattered through the inner solar system. But some molecules, just by random chance, just through the statistics of thousands or millions of molecules all hopping in different directions, happen to make one of their ballistic hops right into a permanently shadowed region at one of the poles. And when a water molecule enters one of those shadows, when it lands on that ultra-cold surface that hasn't seen sunlight in eons, the cold grabs it instantly and doesn't let go. The molecule freezes on contact and becomes part of a growing, accumulating deposit of water ice. This process has been happening for billions of years. Impact after impact, comet after comet, asteroid after asteroid, each one contributing a tiny amount of water. Most of it is lost, but the fraction that makes it into the cold traps stays there, building up slowly, patiently, molecule by molecule, into substantial deposits. It's not just comets, by the way. Certain types of asteroids also carry water, locked up in their minerals as hydrated compounds. When those asteroids impact Mercury, they can also release water, and there might even be water being released from Mercury's own interior in tiny amounts, degassing from ancient minerals deep in the crust when impacts or tectonic fractures crack them open. Every little source contributes to the slow accumulation in the polar shadows. The evidence for this ice is overwhelming at this point. The story of its discovery is actually really fascinating. Back in the early 1990s, astronomers used the giant Arecibo radio telescope in Puerto Rico, that massive dish that sadly collapsed in 2020, to bounce radar signals off Mercury's surface. Radar is a great tool for planetary science because you can do it from Earth and it penetrates straight through any thin atmosphere, though Mercury barely has one anyway, and the return signal tells you about the surface properties. When they looked at the radar returns from Mercury's polar regions, they found something startling. Certain areas, specifically areas inside craters near the poles, produced unusually bright radar returns with very specific characteristics. The signal was highly reflective and had a particular polarization pattern. That signature, that combination of brightness and polarization, is exactly what you get when radar bounces off water ice. Not rock, not metal, ice. The scientists who first saw this data were understandably cautious because the implications were so bizarre. Ice on Mercury? Really? But the signature was unmistakable. Could it be something else? Could rough rock or exposed metal or sulfur deposits somehow produce a similar signal? The team ran through every alternative they could think of, and none of them fit the data as well as water ice. So they published their findings and waited for confirmation or refutation from future missions. That confirmation came decades later when NASA's Messenger spacecraft arrived at Mercury and began its multi-year orbital mission. Messenger carried 3 instruments that could test the ice hypothesis from completely different angles, providing independent lines of evidence. First, a laser altimeter that could trace the exact 3-dimensional topography of Mercury's polar regions with incredible precision. This instrument mapped the shapes and depths of polar craters, identifying precisely which crater floors were truly in permanent shadow based on the sun's geometry and the crater rim heights. Second, a neutron spectrometer, an instrument that could detect hydrogen, the signature element in water. Here's how it works. Cosmic rays from deep space constantly bombard Mercury's surface. When a high-energy cosmic ray hits an atomic nucleus in the soil, it can split that nucleus and release neutrons. Those neutrons scatter through the soil, bouncing off other nuclei. Heavy nuclei like iron don't slow neutrons down much, but light nuclei, especially hydrogen, are very effective at slowing neutrons down through collisions. By measuring the energy spectrum of neutrons coming off Mercury's surface, the neutron spectrometer could effectively sense the presence of hydrogen buried in the soil. and hydrogen, in the context of planetary science, almost always means water. Third, Messenger had visible and infrared cameras that could measure temperatures across the surface, including in shadowed regions using infrared thermal emission. The results from all three instruments agreed beautifully, and that agreement is what makes the case ironclad. Where Earth-based radar had said bright returns that look like ice, the laser altimeter confirmed permanently shadowed regions that never see sun. Where permanently shadowed regions existed, the neutron spectrometer said hydrogen-rich deposits, and where hydrogen was abundant, the temperature measurements confirmed cold enough to keep water ice stable indefinitely. Every line of evidence pointed to the same conclusion. Mercury's permanently shadowed polar craters contain substantial deposits of water ice. In some locations, the ice appears to be relatively pure and bright, sitting right at or very near the surface. In other locations, the ice is buried beneath a thin layer, maybe 10 centimeters or so, of darker material that acts as an insulating blanket. What's that darker material? Scientists think it might be organic compounds, carbon-rich molecules that were also delivered by comets and asteroids. Under the intense radiation environment near Mercury, exposed to solar UV and charged particles from the solar wind, organic molecules can be broken down and polymerized into complex tarry substances that appear very dark. This dark organic lag might protect the brighter ice beneath it from even the tiny amounts of scattered sunlight and thermal radiation that might occasionally sneak into the shadows. The total amount of ice is substantial. Estimates suggest there could be hundreds of billions to potentially trillions of kilograms of water ice tucked away in Mercury's polar shadows. That's enough to fill somewhere between a large lake and a small sea if you gathered it all together. So yeah, the planet closest to the Sun, the one where it's hot enough at noon to melt metal, the one that gets 3 times more solar radiation than Earth does, that planet has ice skating rinks hiding in its shadows. Multiple ice skating rinks, actually, scattered across both polar regions. The universe has a genuinely fantastic sense of irony, and Mercury is one of its best jokes. A planet where you can walk from literally some of the hottest natural surfaces in the solar system to literally some of the coldest within a few kilometers, where the same landscape hosts both furnace and freezer, divided only by whether sunlight can reach a particular spot. It's not just scientifically interesting, it's philosophically delightful. It reminds us that near the sun and hot are not absolute truths everywhere on a planet. Geometry matters. Local conditions matter. A deep crater can create its own microenvironment completely divorced from the planet's average conditions. And from a practical standpoint, if humans ever did want to explore Mercury, despite all the obvious challenges, those polar ice deposits would be incredibly valuable. Water is life support. Water is rocket fuel. If you split it into hydrogen and oxygen, water is radiation shielding. Finding it already there, already collected and concentrated by billions of years of natural processes, would be a tremendous asset. Mercury's ice is proof that the solar system is full of surprises, that reality is more creative than our assumptions, and that even the most extreme environments can hide pockets of the unexpected, if you just know where to look and understand the geometry, the messenger that moves like quicksilver. Before we dive into the really weird stuff, let's talk about how Mercury got its name, because even that tells you something important about this world. The ancient Romans looked up at the sky and noticed 5 wandering stars that moved against the background of fixed constellations. These were the 5 planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. Each one got named after a god, and the names were chosen deliberately to match each planet's most obvious characteristic. Mercury, that tiny spark of light that appears briefly near the horizon, just after sunset or just before sunrise, was named after the Roman god Mercury, the divine messenger. You know the one, young, quick, wearing those famous winged sandals, always darting from place to place, carrying messages between the gods and mortals. The name fits absolutely perfectly. Mercury, the planet, is fast, genuinely, remarkably fast. It orbits the Sun at an average velocity of about 47 kilometers per second. That's over 170,000 kilometers per hour. To put that in perspective, Earth plods along at a comparatively leisurely 30 kilometers per second. Mercury is sprinting. Why so fast? It's all about orbital mechanics and gravity. The closer you are to the Sun, the deeper you sit in its gravitational well, and the faster you have to move to maintain orbit. It's like how water circles faster and faster as it approaches the drain in your bathtub. Mercury, being the innermost planet, sitting at the very bottom of the Sun's gravitational slope, has no choice but to race. That 88-day orbital period is remarkable. Think about it. While Earth is slowly working its way through spring, Mercury has already completed an entire year, 4 times. By the time we've gone through all 4 seasons and returned to the same point in our calendar, Mercury has orbited the Sun more than 4 times. The ancient astronomers who tracked Mercury's movements in the sky knew it was special. It never strayed far from the Sun. It appeared in the morning sky for a few weeks, then disappeared, then reappeared in the evening sky for a few weeks, then vanished again, playing this endless game of peekaboo with observers. Some ancient cultures initially thought they were seeing 2 different objects, a morning star and an evening star. Eventually, careful observation revealed the truth. It was one world alternating between morning and evening appearances as it orbited inside Earth's path. The Greeks called it Hermes in the morning and Apollo in the evening before realizing their mistake. The Babylonians tracked it obsessively, creating detailed tables of its appearances and disappearances. To predict Mercury's behavior required careful record-keeping, mathematical skill, and patience. No wonder they associated it with Nabu, their god of wisdom and writing. But here's where things get really interesting, where Mercury starts to reveal its paradoxical nature. The planet, where a day lasts longer than a year. Mercury is the fastest planet in orbit, racing around the Sun every 88 days. But when it comes to rotation, when it comes to turning on its own axis and experiencing a day-night cycle, Mercury is unbelievably, almost impossibly slow. If you were somehow standing on Mercury's surface, perhaps sheltered inside a heavily shielded habitat, and you watched the Sun slowly move across that black, star-filled sky, you would be standing there watching for 176 Earth days. That's right. One single Mercurian solar day, the time from one noon to the next noon, from the moment the Sun is highest in the sky until it returns to that same position, lasts 176 Earth days. Let me say that again because it's genuinely hard to wrap your mind around. One day on Mercury is longer than 2 Mercurian years. How is that even possible? How can a year be shorter than a day? It seems to violate basic logic. It all comes down to an absolutely elegant piece of celestial mechanics called a 3-2 spin-orbit resonance. This is where Mercury really starts to show off its mathematical precision. For every 2 complete orbits Mercury makes around the Sun, it rotates exactly 3 times on its axis. Not approximately 3 times. Not roughly 3 times. Exactly 3 times. It's locked into this precise rhythm through billions of years of tidal interactions with the Sun. Let me break down how this creates such a long day. Mercury rotates once every 58.6 Earth days relative to the distant stars. That's called a sidereal day. But because Mercury is also moving rapidly along its orbit, and in the same direction it's rotating, the Sun's apparent position in the sky changes much more slowly than the planet's rotation would suggest. It's similar to how, on Earth, the Sun doesn't return to the same position in the sky every 23 hours and 56 minutes. which is how long Earth takes to rotate relative to the stars. Instead, our solar day is 24 hours because Earth has moved a bit along its orbit, requiring about 4 extra minutes of rotation for the Sun to return to the same spot overhead. On Mercury, this effect is extreme. The planet's fast orbital motion, combined with its slow rotation, creates a huge difference between the sidereal day and the solar day. The math works out to exactly 176 Earth days from noon to noon. But wait, it gets weirder. Much weirder. Because Mercury's orbit isn't a perfect circle but rather an elongated ellipse, the planet doesn't move at constant speed. When Mercury swings close to the Sun at perihelion, its closest approach, it speeds up dramatically. At its farthest point, aphelion, it slows down. This is just basic orbital mechanics. Following Kepler's laws, every planet on an elliptical orbit does this. But on Mercury, something bizarre and almost surreal happens because of the combination of that elliptical orbit and that 3-2 resonance. In certain regions of Mercury's surface, particularly in 2 broad longitude bands on opposite sides of the planet, the orbital speed at perihelion actually exceeds the rotational speed. For a brief period, Mercury is moving around the Sun faster than it's spinning, and from the perspective of someone standing in one of these special zones, that creates one of the most bizarre astronomical phenomena in the entire solar system. The Sun appears to slow down as it approaches the meridian, the highest point in the sky. Then it stops. It just hangs there, motionless, for what would be several Earth days. Then impossibly, it starts moving backward, drifting in reverse across the sky. Then it pauses again, gathering itself, and finally, it resumes its forward march. Imagine experiencing a sunrise that takes not minutes or hours, but literal weeks to complete. You watch the Sun slowly, almost imperceptibly, crawl up over the horizon. If you were patient enough to sit and watch a boulder's shadow, you might see it move a few centimeters per hour. That's how slow Mercury's dawn is. Then noon arrives after months of waiting, but it's not a normal noon. The Sun now appearing about 3 times larger than we see it from Earth because Mercury is so much closer, hovers near its highest point, and then it hesitates. For someone in the right location, the Sun would appear to stop, drift slightly backward in the sky, over several Earth days, pause again, and then finally continue forward. It's like the universe's slowest instant replay. And then, after this cosmic hesitation, the Sun continues its journey across the black, star-filled sky. There's no blue to the sky on Mercury, no atmosphere to scatter sunlight, so even at noon the stars are visible, sharp and clear. The Sun itself is a brilliant, harsh white disk, larger and more intense than anything we experience on Earth, moving with glacial patience toward the western horizon. Eventually, after months of this slow procession, sunset arrives, and like sunrise, it's not a brief event, it's a prolonged dimming that takes weeks. Shadows lengthen over the course of Earth days. The landscape gradually shifts from the intense illumination of full daylight to the absolute darkness of night, and then, finally, night falls. But night on Mercury isn't a quick interlude before the next day. It lasts for 88 Earth days, nearly 3 Earth months of continuous darkness, during which the ground radiates away all the heat accumulated during the long day. Temperatures plummet from over 400 degrees Celsius to below negative 170 degrees Celsius. The same rock can experience a temperature swing of nearly 600 degrees from day to night. That's the most extreme temperature variation of any planet in the solar system. And then, after those long months of darkness, dawn begins its slow return. The process repeats. Week after week of gradually brightening sky, the Sun finally peaks over the horizon. Shadows start their months-long retreat across the landscape. That's what time feels like on Mercury. It's a world where patience isn't just a virtue, it's the only way to experience anything. A world where you could watch geological processes that normally take years happen during a single day-night cycle, simply because that cycle is so incredibly long. The planet that's basically a metal ball with a thin rock coating. Now let's talk about what Mercury is actually made of, and this is where the planet's strangeness really starts to become apparent. Because Mercury isn't just unusual in how it moves, it's deeply weird in what it is. Most planets, not just in our solar system but probably throughout the universe, are built according to a pretty standard recipe. You've got a relatively thin outer crust, the solid skin that we see and walk on. Beneath that is a thick mantle of denser rock, the bulk of the planet's volume, and at the very center there's a metallic core, usually made of iron and nickel, that makes up a modest fraction of the planet's total mass. Earth works this way. Our crust is thin, maybe 30 to 40 kilometers thick on average. Our mantle extends down almost 3,000 kilometers, making up about 84% of Earth's volume, and our core, while substantial, accounts for only about 32% of Earth's mass. We're a rocky planet with a metal center. The rock dominates. Mars follows a similar pattern. Venus follows a similar pattern. The Moon follows a similar pattern. It's planetary architecture, 101. It's how terrestrial worlds are supposed to be built. Mercury looked at that standard recipe and threw it in the trash. Get this, approximately 70% of Mercury's entire mass is just its iron-nickel core. 70%. 7 out of every 10 grams of mercury is metal, not rock. If you could somehow slice the planet perfectly in half like a cosmic grapefruit, exposing its interior layers, you'd see that the metallic core takes up roughly 85% of the planet's radius. The rocky outer layers, the silicate mantle and the thin crust, are basically just a shell, an almost afterthought, a thin coating stretched over what is fundamentally a gigantic ball of iron. To put this in perspective, imagine building a model of Mercury. If you made the whole planet the size of a basketball, the metal core would be the size of a volleyball. The rock layers would be less than 2 centimeters thick all the way around. That's the proportion we're talking about. Mercury is less a rocky planet with a metal core and more a metal ball with a rock veneer. This is genuinely bizarre. This is not how planets are supposed to form. This is not what planetary formation models predict should happen when you condense rock and metal out of a disk of dust and gas around a young star. Earth has a substantial iron core, and it's responsible for crucial things like our magnetic field, and probably plays a role in plate tectonics. But even with our large core, rock still makes up about 68% of Earth's mass. Earth is fundamentally a rocky world that happens to have metal inside. Mercury is fundamentally a metal world that happens to have rock outside. It's like someone at the cosmic factory was building planets on an assembly line, working through the standard process, and when they got to Mercury, they accidentally reversed the recipe, like they read the instructions backward, or like someone ordered just the planetary core from the catalogue and completely forgot to add enough actual planet around it before shipping it off to orbit the Sun. So what in the world happened? How did Mercury end up with these completely reversed proportions? Why is this planet so metal-rich compared to everything else? Scientists have been puzzling over this question for decades, and I mean seriously puzzling over it. This isn't just a curiosity, it's a fundamental mystery about planetary formation, and over the years, several competing theories have emerged to explain Mercury's bizarre composition. The first major idea is called the giant impact hypothesis, and it's dramatic. Picture the early solar system, about 4.5 billion years ago. Things were chaotic. The planets were still forming, still accreting mass, still clearing out their orbital neighborhoods. There were lots of large planetary embryos, protoplanets, wandering around on unstable orbits, occasionally running into each other. In this scenario, there was once a proto-Mercury that was significantly larger than the current planet, maybe 50% or even 100% larger, with more normal Earth-like proportions of rock to metal. It had a substantial iron core, yes, but it was wrapped in a thick, healthy silicate mantle, just like a regular terrestrial planet should be. And then, catastrophe. Another planetary body, something massive, perhaps Mars-sized or larger, slammed into proto-Mercury at enormous velocity. The collision was so energetic, so utterly catastrophic, so mind-bogglingly violent, that it didn't just crater the surface, it literally stripped away most of the rocky mantle, blasting thousands of kilometers of silicate rock into space as superheated vapor and debris. What was left behind after this cosmic mugging? The dense iron-nickel core, too heavy to be blown away, too gravitationally bound to escape, plus just a thin remnant of the original silicate mantle, a surviving fraction of the rock that used to surround the metal center. It's planetary strip mining by asteroid impact. It's liposuction performed with kinetic energy. It's one of the most violent scenarios in planetary science, and it would explain why Mercury is so unusually metal-rich. But there's a problem with this idea. Well, several problems actually. First, where did all that stripped away rock go? That's a lot of material to just disappear. Some of it would have escaped the inner solar system entirely. Some might have fallen into the sun. Some might have eventually reaccreted onto Mercury or other planets. But tracking all that material is difficult. Second, and this is more serious, Mercury's surface composition doesn't quite fit the story of something that was utterly devastated by a giant impact. When NASA's Messenger spacecraft analyzed Mercury's crust, it found something surprising: significant amounts of volatile elements like sulfur, potassium, and sodium. These are relatively fragile elements, the kind that should have been completely vaporized and lost if Mercury experienced the kind of superheated, ultraviolent collision that the giant impact hypothesis requires. It's like finding ice cream intact after your house burned down. The volatiles shouldn't be there if the impact was hot and violent enough to strip away thousands of kilometers of rock. So scientists started looking at alternative explanations, or at least modifications to the impact theory. The second major idea focuses on where Mercury formed rather than what hit it. This is called the nebula fractionation hypothesis, and it's more subtle. In this scenario, the early solar nebula, that disk of gas and dust swirling around the young sun, wasn't chemically uniform. Different regions had different compositions. Close to the sun, temperatures were incredibly high. We're talking thousands of degrees Kelvin. In that extreme heat, certain materials could condense out of the nebula gas and form solid grains, while other materials remained vaporized. Metals like iron have high condensation temperatures. They can solidify even in extremely hot environments. But silicate minerals, the rocky materials that make up planetary mantles and crusts, have lower condensation temperatures. They need it to be cooler before they'll form solid grains. In the hottest part of the solar nebula, very close to the sun, maybe only metal grains could form. Farther out, where it was cooler, both metal and rock could condense. So the innermost region of the disk, where Mercury was forming, naturally had a higher ratio of metal to rock, simply because rock couldn't condense there as easily. Add to this some additional fractionation processes. Sunlight exerts radiation pressure on small dust grains, and it pushes different types of grains differently depending on their size and composition. This is called photophoresis. Magnetic fields in the early nebula might have shepherded metallic grains towards certain regions while leaving silicate grains behind. There are all sorts of complex processes that could have sorted materials by composition in the inner solar system. The result would be a planet that naturally accreted more metal than rock, simply because that's what was available in its neighborhood. Mercury's composition would be a direct reflection of the chemical geography of the early solar nebula. This idea explains Mercury's metal richness without requiring a catastrophic impact. It's gentler, more gradual, more about cosmic chemistry than cosmic violence. But it has its own problems. Most notably, it struggles to explain how Mercury could have retained as many volatile elements as it has. If the inner solar system was hot enough to fractionate metal from rock, it should have been hot enough to boil away volatiles completely. Yet there they are, on Mercury's surface, stubbornly present when they shouldn't be. So what's the truth? What really happened? Most planetary scientists today think the answer is probably a messy combination of both scenarios, plus some additional factors we haven't even discussed yet. Maybe Mercury formed in a metal-rich region of the solar nebula, giving it unusual proportions from the start. Then maybe it experienced one or more glancing impacts, not necessarily a single catastrophic collision, but a series of hit-and-run encounters, where impactors stripped away some of the silicate mantle, but didn't completely destroy the planet or vaporize everything. These hit-and-run impacts are gentler than head-on collisions, leaving more material intact while still removing enough rock to shift the proportions even further toward metal. And maybe the young sun helped. The early sun went through what's called the T-Tauri phase, a period of intense stellar activity with powerful stellar winds and bursts of radiation. These winds could have blown away lightweight debris from the inner solar system, preventing stripped-away silicate material from falling back onto Mercury, while the denser metallic core remained firmly in place. Add all these factors together, season with 4.5 billion years of additional impacts and evolution, and you end up with Mercury as we observe it today, a compact, dense, metal-dominated world with just enough rock on the outside to be interesting and just enough volatiles preserved to confuse our neat theories. Whatever the exact sequence of events, one thing is absolutely clear. Mercury's formation story was not simple. The inner solar system did not hand out ingredients fairly or uniformly. Some locations in that swirling disk of dust and gas were richer in certain materials than others. Mercury formed in a special neighborhood, a place where metal was abundant and rock was relatively scarce, or where violent early events sculpted its proportions into something unusual. And the result is a planet that teaches us something profound. Planetary formation is messy, chaotic, and full of local variations. Every planet is shaped not just by universal laws of physics, but by the specific, unique, contingent history of the particular part of the disk where it happened to form. Mercury isn't a failed planet. It's not a mistake. It's a perfectly valid outcome of planetary formation under a specific set of initial conditions. It's what you get when you form a terrestrial world very close to a star, in a region that for whatever combination of reasons ended up being unusually metal-rich. And that makes Mercury valuable, not despite its weirdness, but because of it. Every time we study Mercury, every measurement we make, every high-resolution image we capture, we're gathering clues about what the innermost solar system was like during those chaotic first few 100 million years. We're reading a story written in iron and rock about conditions and processes that no longer exist, that were erased everywhere else, but that Mercury has preserved in its very structure. Mercury is a time capsule. It's a message in a bottle from the earliest days of our solar system. And the message says, things were wild back then, wilder than you can imagine, and the planets you see today are the survivors of that chaos, each one shaped by forces and accidents that will never be fully reconstructed, but can be glimpsed, inferred, and marveled at in the details that remain. The wrinkles in time, Mercury's mysterious lobate scarps tell deeper stories. We've already talked about Mercury's lobate scarps, those enormous cliff faces that formed as the planet shrank over billions of years. But there's more to these features than just simple contraction. When scientists looked more closely at the patterns, The orientations, the relationships between different scarps, they found something unexpected. The story is more complex than just a uniformly shrinking planet. Some lobate scarps are truly ancient, cutting through the oldest, most heavily cratered terrain on Mercury's surface. These are the scars from Mercury's earliest cooling, from when the planet's interior was losing heat most rapidly, when contraction was happening fastest. They're deeply degraded in places, softened by billions of years of subsequent impacts that have blurred their once sharp edges. Other scarps are remarkably fresh, cutting through relatively young volcanic plains with crisp, sharp edges that cast clean shadows. These formed later, when Mercury's cooling had slowed but hadn't stopped entirely. The planet was still settling, still adjusting, still squeezing its crust to accommodate its shrinking core. And here's something fascinating. The distribution of scarps isn't random. When researchers mapped every major lobate scarp they could find and analyzed their orientations, looking for patterns in which direction different scarps faced and how they were arranged across the planet, they found hints of a global pattern. Some of this pattern might relate to Mercury's enormous iron core and how it cooled. The core probably didn't cool uniformly in all directions. Temperature variations, compositional differences, or asymmetries in how heat escaped through the mantle above could have created preferential directions of contraction. The crust responded by forming scarps that aligned with those stress patterns, creating a subtle global network of compression features that tells a story about what was happening deep below. There are also places where multiple scarps intersect or run parallel to each other, creating complex networks of faults. These areas probably experience particularly intense compressional stress, perhaps because of local variations in crustal thickness or strength, or because they were located at particularly vulnerable spots in Mercury's stress field. Standing on Mercury and looking at these scarps, you'd see more than just cliffs. You'd see a landscape actively shaped by internal forces, a surface that recorded billions of years of thermal evolution in permanent stone. Every scarp is a timestamp, marking a moment when the stresses in the crust exceeded the rock's strength and something had to give. And Mercury, patient Mercury, has preserved every one of those moments. The strange case of Mercury's missing mantle. Let's circle back to that central mystery one more time, because it really is the key to understanding everything unusual about Mercury. This planet should have more rock, much more rock. Where did it go? Even if we accept some combination of the formation theories we discussed, there's still something deeply puzzling when you compare Mercury's composition to computer models of planetary formation. Most simulations that try to build rocky planets from a disk of dust and gas around a young star naturally produce worlds with what we'd call normal proportions, roughly 30 to 40% metal core, the rest rocky mantle and crust. Getting Mercury's extreme 70% metal composition requires something exceptional, something that violates the average conditions in the disk. You need special pleading, special circumstances, an unusual event or an unusual environment. And that tells us something profound about how planets actually form in real star systems, as opposed to idealized computer models. Real planetary systems are messy. They're full of local variations, random events, chaotic encounters, and unique conditions that never repeat exactly the same way twice. Jupiter's gravitational influence, for example, probably stirred up the entire solar system during its formation and early migration. Giant planets, moving through a disk of material, can create waves, resonances, zones of clearing, and regions of concentration. Maybe Jupiter's early behavior created a metal-rich ring or concentration zone right where Mercury was forming, purely by accident of orbital dynamics. Or maybe there was a population of iron-rich planetimals, building blocks left over from the very earliest condensation in the hottest part of the nebula, and Mercury happened to form in just the right place to sweep up more of those than it swept up of the rocky planetesimals that were more common, slightly farther out. The point is, Mercury's composition is teaching us that planet formation is not a deterministic, predictable process that always produces the same results from the same initial conditions. It's a stochastic, contingent process full of randomness and local variations. Every planetary system will have its own quirks, its own oddballs, its own outliers that formed under unusual circumstances. Mercury is our local oddball, and we're lucky to have it because it's teaching us that planetary diversity is real, that unusual outcomes are possible, and that we should expect to find even stranger things when we eventually study exoplanets around other stars in detail. There are probably other star systems out there with their own Mercury analogues, planets that ended up metal-rich through their own unique circumstances, and there are probably planets even stranger than Mercury, with compositions we haven't even imagined yet, formed under conditions that never occurred in our solar system. Mercury is a reminder that the universe is creative, that planetary formation explores a wide range of possibilities, and that the unexpected is not just possible but likely once you start looking closely enough. The symphony of elements, Mercury's chemical fingerprint. When Messenger spacecraft spent 4 years in orbit around Mercury, one of its most important jobs was chemical analysis. Using X-ray and gamma-ray spectrometers, instruments that could detect the characteristic radiation signatures of different elements, Messenger built up a detailed map of Mercury's surface composition. And that composition is genuinely weird, distinctive, unlike anything we've seen on other terrestrial planets. It's Mercury's chemical fingerprint, unique in the solar system. First, as we've mentioned, Mercury's surface is unusually low in iron for a rocky planet. On Earth, the Moon, Mars, Venus, typical volcanic rocks and crustal materials, are rich in iron-bearing minerals. Iron gives basaltic rocks their dark color and their relatively high density. But Mercury's surface materials are relatively iron-poor. The iron is mostly locked away in that enormous core, not spread throughout the crust. Second, Mercury is rich in sulfur. Remarkably, surprisingly rich. Sulfur abundances in Mercury's crust are several times higher than what we measure on the Moon or Mars. That sulfur is probably present as sulfide minerals, compounds where sulfur has bonded with metals like iron, calcium, or magnesium. Why so much sulfur? It goes back to those reducing conditions during formation. In an oxygen-poor environment, sulfur becomes much more chemically important. It bonds readily with metals and gets incorporated into minerals rather than getting oxidized and lost as gaseous compounds. Third, Mercury has high concentrations of certain volatile elements that really shouldn't be there in such abundance. Elements like potassium, sodium, and chlorine. These are called volatiles because they evaporate relatively easily at high temperatures. They should have been baked out of the inner solar system during planet formation, especially this close to the Sun. And yet there they are, stubbornly present on Mercury's surface in amounts comparable to or even higher than what we find on Earth or Mars. Potassium in particular is abundant, way more abundant than simple models of inner solar system chemistry predict. This is actually one of the strongest pieces of evidence against the most extreme versions of the giant impact hypothesis. If Mercury had been completely vaporized, if its surface had been heated to thousands of degrees by a massive collision, volatiles would have been lost. They would have evaporated into space, never to return. The fact that they're still there tells us that whatever happened to Mercury during its formation and early evolution, the process wasn't so violent or so hot that it completely stripped away these fragile elements. Maybe impacts were glancing rather than head-on. Maybe vaporization was incomplete. Maybe some volatiles were delivered later, after the violent era ended, by comets or volatile-rich asteroids. Fourth, Mercury's surface has unusual abundances of certain refractory elements, elements that condense at very high temperatures and resist evaporation. Elements like calcium, aluminum, and titanium show distinctive patterns that give clues about what minerals are present and how the crust formed. Messenger also found dark patches on Mercury's surface, regions with very low reflectance, much darker than the surrounding terrain. These dark deposits are associated with impact craters and volcanic vents, and they appear to be rich in carbon and other light elements. They're called low reflectance material, or LRM, and they're probably graphite or some other carbon-rich substance that was either delivered from space by impacts or brought up from depth by volcanic eruptions. The presence of so much carbon, like the presence of so much sulfur, reinforces the picture of Mercury as a chemically reducing world where elements that would normally be oxidized or lost in other environments have been preserved and concentrated. All of these chemical signatures together paint a picture of Mercury as a world that formed under conditions quite different from Earth, Mars, or Venus. It's not just a smaller version of Earth, it's its own distinct type of terrestrial planet, with its own geochemical personality. And that chemical personality is preserved remarkably well because Mercury lacks the processes that would remix or erase it. No plate tectonics to recycle the crust, no weathering to break down minerals, no oceans to dissolve and transport elements. What formed billions of years ago is still there, on the surface, readable, waiting for spectrometers to measure it and scientists to interpret it. Mercury is like a planetary fossil, chemically frozen in time, offering us a window into conditions and processes from the very beginning of the solar system. The vanished atmosphere that never was. Let's talk for a moment about what Mercury doesn't have, because that absence is just as informative as what it does have. Mercury doesn't have a proper atmosphere. It has what's called an exosphere, an incredibly thin envelope of atoms bouncing around above the surface, but calling that an atmosphere is generous to the point of being misleading. It's more like outer space with very slightly more atoms in it than usual. The pressure at Mercury's surface is about 10 to the negative 15 times Earth's atmospheric pressure. That's 1/4,000,000th of our air pressure. For all practical purposes, Mercury's surface is exposed directly to the vacuum of space. Why doesn't Mercury have an atmosphere? 3 main reasons, all working together. First, Mercury is small, which means its gravitational pull is weak. Escape velocity on Mercury is only about 4.3 kilometers per second, compared to Earth's 11.2 kilometers per second. That makes it much easier for gas molecules to gain enough speed to escape into space permanently. Second, Mercury is hot. On the day side, temperatures soar high enough that most molecules are moving very fast, and fast molecules are more likely to reach escape velocity. Even gases that would be liquid or solid at Earth's temperatures are hot gases on Mercury, zipping around rapidly, ready to flee. Third, and perhaps most importantly, Mercury is absolutely blasted by the solar wind and solar radiation because it's so close to the sun. High-energy photons from the sun can strike atoms in any potential atmosphere and kick them hard enough to escape. The solar wind, that stream of charged particles constantly flowing off the sun, literally pushes on atmospheric particles and sweeps them away. Mercury has a weak magnetic field that provides some protection by deflecting some of the solar wind around the planet, rather than letting it hit the surface directly. But that protection is minimal, nowhere near enough to shield a full atmosphere, the way Earth's much stronger magnetic field protects our air. The result is that any atmosphere Mercury might have had, any gases that might have been released during its formation or delivered later by comet impacts, has been stripped away over time, molecule by molecule, until almost nothing remains. What's left is the exosphere, a tenuous collection of atoms that are constantly being replenished and lost in a dynamic balance. Atoms are released from the surface by several processes. Impacts kick up material, solar wind particles hit the surface and sputter atoms away, sunlight heats certain minerals enough to release trapped gases, and occasionally particles from the sun itself chemically react with surface materials and release atoms. Those released atoms bounce around for a while, making long ballistic hops across the surface in the low gravity. Eventually, most of them either gain enough energy to escape entirely, or they land back on the surface and stick there, temporarily removed from the exosphere until something releases them again. Messenger measured the composition of Mercury's exosphere and found it contains mostly sodium and potassium atoms, along with hydrogen, helium, oxygen, calcium, magnesium, and traces of other elements. The sodium is particularly noticeable because it glows in sunlight, creating a faint sodium tail that extends behind Mercury like a comet's tail, visible from Earth with sufficiently sensitive telescopes. But even adding up all those atoms, the total amount of gas is incredibly tiny. If you could somehow gather all the atoms in Mercury's exosphere into a single bubble, that bubble would still be a much better vacuum than the best vacuum chambers we can create in laboratories on Earth. So Mercury is essentially airless, exposed, naked to space, and that has profound implications for everything else. Without an atmosphere, there's no weathering. On Earth, wind and rain and ice constantly break down rocks, grinding mountains into sand, transporting sediment, creating soils. On Mercury, none of that happens. A rock on Mercury's surface will sit unchanged, except for the occasional meteorite impact, for billions of years. The surface is geologically static, in a way that's almost impossible on Earth. Without an atmosphere, there's no sound. Thunder doesn't exist. Wind doesn't exist. A landslide on Mercury would be completely silent, visible but inaudible, because there's no air to carry pressure waves. Without an atmosphere, there's no erosion of impact craters. Craters on Earth get worn down, filled in, eroded away within millions of years or faster. Craters on Mercury stay sharp and fresh-looking for billions of years unless another impact hits them directly. Without an atmosphere, there's no twilight. On Earth, the sun can be below the horizon and we still have light because the atmosphere scatters sunlight. On Mercury, sunset is instant. The sun drops below the horizon and boom, darkness. Stars become visible immediately. There's no gradual transition. Without an atmosphere, temperatures swing wildly between extremes. Air acts as insulation, transporting heat from hot regions to cool regions, moderating temperature differences. On Mercury, there's nothing to transport heat except thermal conduction through the rock itself, which is slow and inefficient. Each point on the surface is thermally isolated from its surroundings. Hot places stay hot, cold places stay cold, and the transition between them is sharp and dramatic. So, Mercury's lack of atmosphere isn't just a minor detail. It fundamentally shapes the planet's character, its behavior, its appearance, everything about how it works. It makes Mercury more lunar than Earth-like, more asteroid than planet in some ways, despite being large enough to be spherical and differentiated. And it creates that wonderful paradox we talked about at the very beginning. A planet hot enough to melt metal at noon can have permanent ice at the poles, because there's no atmosphere to transport heat between those two extremes. They exist in the same world but in completely different thermal universes. When worlds collide, the cratered canvas of deep time, let's talk about impacts, because Mercury's surface is absolutely covered with them, a canvas painted layer upon layer with circular scars of cosmic violence spanning billions of years. When you look at high-resolution images of Mercury, the first thing that strikes you is how similar it looks to our moon. Craters. Craters everywhere. Craters of every size, from enormous multi-ring basins, hundreds of kilometers across, down to tiny pits, barely a few meters wide. Craters on top of craters. Craters inside craters. Craters overlapping craters in complex palimpsets, where later impacts have partially erased earlier ones. creating intricate patterns that require careful analysis to untangle. This is the signature of an ancient surface preserved without erosion. Every impact that's happened since the crust first solidified is potentially still visible somewhere, unless it's been buried by lava flows or erased by subsequent impacts. The Moon looks similar because it shares those characteristics. No atmosphere, no weathering, no plate tectonics, just passive accumulation of impact scars over billions of years. But Mercury's cratering record is even more intense, even more densely packed, because Mercury sits deeper in the Sun's gravitational well, and therefore gets hit more frequently. Objects falling into the inner solar system, asteroids whose orbits have been perturbed, comets swinging in from the outer reaches, all of them are more likely to encounter Mercury than more distant planets, simply because Mercury's orbit sweeps through a larger volume of space over time. It's like Mercury is sitting near the entrance to a shooting gallery, first in line to intercept anything heading sunward. And those impacts are faster, more energetic, because impactors have accelerated deeper into the Sun's gravity well before they hit. Typical impact velocities on Mercury are around 40 to 50 kilometers per second, compared to about 20 kilometers per second for Earth. Higher velocity means more kinetic energy, which means more explosive impacts, which means larger craters from the same size impactor. Mercury's lower gravity partly compensates for this. Lower gravity means ejecta can travel farther and crater rims don't have to support as much weight, which changes some of the scaling relationships. But overall, Mercury has taken a real beating, a sustained bombardment that's been ongoing for the entire age of the solar system. The oldest surfaces on Mercury date back about 4 billion years, to the tail end of what's called the Late Heavy Bombardment, a period when the entire inner solar system experienced an intense spike in impact rates. The cause of this bombardment was probably a gravitational instability in the outer solar system, where the orbits of Jupiter and Saturn shifted slightly, stirring up populations of asteroids and comets, and sending them careening into the inner system where they pummeled everything in sight. Mercury bears the scars of that ancient assault. Its most heavily cratered regions, the ancient highlands, are saturated with overlapping impact scars, pocked and battered to the point where almost every square meter of surface has been disturbed by impacts at some point. But not all of Mercury's craters are ancient. The impact process continues today, just at a much slower rate than during that early bombardment. Fresh craters with sharp rims and bright ray systems, ejecta patterns radiating outward from the impact site, appear scattered across the surface. These are recent impacts, recent in geological terms, meaning anywhere from a few million to perhaps a few 100 million years old. The brightest and freshest crater on Mercury is a feature named Hokusai, a spectacular impact scar about 114 kilometers in diameter, surrounded by the most extensive ray system on the planet. Brilliant streaks of ejected material, pulverized rock thrown out by the impact and deposited in long lines radiating from the crater, extend for more than 1,000 kilometers in every direction. Under certain lighting conditions, Hokusai and its rays dominate an entire hemisphere of Mercury, a cosmic artwork visible from millions of kilometers away. These bright rays are fresh material excavated from below the surface by the impact. Mercury's surface is constantly being darkened over time by a process called space weathering, where solar wind particles and micrometeorite impacts gradually alter the optical properties of surface materials, making them darker and redder. Fresh material brought up by a new impact hasn't been space weathered yet, so it appears bright, creating those distinctive rays. Over millions of years, those rays will gradually fade as space weathering darkens the ejected material to match the surrounding terrain. Eventually, the rays disappear, leaving just the crater itself. That's why older craters don't have ray systems, even though they probably did when they first formed. Some of Mercury's impact craters have central peaks, mountains that rise up in the middle of the crater floor, formed when rock rebounded after the impact, like a splash frozen in stone. Others have terraced walls where the crater rim collapsed inward in a series of steps, unable to support its own weight. The largest craters have multiple rings, concentric circular features surrounding the main crater, formed by waves of rock that rippled outward through the crust during the impact like waves on a pond but frozen into permanent topography. The Caloris Basin, which we've already mentioned, is the most spectacular example of this. It's one of the youngest large impact basins on Mercury, probably about 3.8 to 3.9 billion years old, formed during the tail end of the late heavy bombardment. The impact that created Caloris was so enormous, so incredibly violent, that it had global consequences. On the opposite side of Mercury, directly antipodal to Caloris, there's a region of weird, jumbled, broken-up terrain called the weird terrain, or chaotic terrain by geologists. This isn't a creative name, it's literally just descriptive, because nobody could figure out what process could create such a strange landscape. Eventually, scientists realized that this weird terrain formed as a direct result of the Caloris impact. When that massive impactor hit Mercury, it sent seismic waves, planet-shaking vibrations, traveling through the entire body of the planet. Those waves traveled along the surface and through the interior, radiating outward in all directions. On the side where the impact happened, the waves were traveling outward, moving away from the impact site, so they gradually weakened and dispersed. But on the opposite side of the planet, all those waves converged, all focused on a single point directly opposite the impact, and when they met, they reinforced each other. Imagine dropping a rock into the exact center of a perfectly circular pond, waves spread outward. When they reach the edge of the pond, they reflect back toward the center, and when they meet in the middle again, they interfere, creating a zone of amplified wave action. The same thing happened inside Mercury. Seismic waves from the Caloris impact focused at the antipodal point, creating intense ground motion, shaking, perhaps even liquefaction of surface materials. The crust fractured into a chaotic jumble of broken blocks, ridges, and valleys. The landscape was literally shaken apart by seismic energy that had traveled halfway around the planet. That's how violent the Caloris impact was. It didn't just excavate a giant crater, it broke the surface on the opposite side of the planet. It was a globally significant event, a catastrophe that temporarily reshaped Mercury's geology. And yet Mercury survived. It absorbed that impact, incorporated that crater into its landscape, moved on. 4 billion years later, Caloris is still there, weathered by subsequent impacts, partially filled with volcanic plains, but recognizable, permanent, a monument to ancient violence now preserved in eternal calm. The Hollows, Mercury's most recent mystery. Among all of Mercury's fascinating features, one of the most recently discovered and least understood is a type of terrain that nobody predicted, nobody expected, and that still puzzles scientists years after Messenger first spotted them. The Hollows. These are small, irregular, shallow depressions scattered across certain regions of Mercury's surface, particularly around impact craters and in areas where fresh material has been exposed. They're bright, much brighter than the surrounding terrain, giving them a distinctive appearance in images. They're rimless, meaning they're not impact craters with raised edges. They're flat-bottomed, and they're often clustered in groups, creating Swiss cheese-like textures across the affected areas. When Messenger scientists first noticed these features in high-resolution images, they didn't immediately know what they were looking at. The features were too small and too shallow to be impact craters. They didn't look like volcanic vents. They didn't match any known geological process on other planets. Eventually, through detailed analysis and comparison with different wavelength observations, a picture emerged. The hollows appear to be actively forming today. or at least formed very recently in geological terms, through a process that's removing material from the surface. The leading hypothesis is that the hollows are created by sublimation, the direct transition of a solid material into gas without passing through a liquid phase like dry ice evaporating. Specifically, Mercury's surface apparently contains small amounts of volatile rich minerals, compounds that are stable at normal temperatures, but that break down and release gas when exposed to Mercury's extreme dayside heat and intense solar radiation. When an impact or tectonic activity exposes fresh material containing these volatile minerals, the sun's heat and ultraviolet radiation hit them. The minerals begin to break down chemically, releasing gas molecules. Those gases escape into Mercury's exosphere and are eventually lost to space. And where the minerals decomposed, a hollow remains, a small pit left behind where solid material turned to gas and vanished. This process is called space weathering sublimation, and it's apparently ongoing. Computer estimates of how quickly it should happen suggest that some hollows could be forming or expanding right now, making them some of the youngest geological features on Mercury, younger even than the most recent impact craters. That's genuinely remarkable. On a planet that's supposedly geologically dead, where volcanism ended billions of years ago, and where the dominant surface processes are all impact-related, there's apparently still an active process carving fresh features into the landscape, not driven by internal heat, not driven by tectonics, but driven by the sun's relentless radiation breaking down minerals that shouldn't be stable on an airless world, this close to our star. The exact composition of the volatile rich minerals responsible for hollow formation is still debated. Likely candidates include sulfides, minerals where sulfur is bonded to metals like iron or calcium, that break down under solar radiation and heat. Mercury's high sulfur abundances make sulfides a plausible culprit. Other candidates include chlorides or carbon-bearing compounds. Whatever the exact chemistry, the hollows are teaching us that Mercury's surface is more dynamic, more active, and more responsive to its environment than we thought. Even without geological activity in the traditional sense, without magma rising or plates shifting, Mercury is still changing, still evolving, still writing new chapters in its surface history through chemical processes driven by its harsh environment. If you could visit Mercury and observe the hollows up close, you'd be looking at one of the most recently formed features not just on Mercury, but in the entire inner solar system. You'd be watching, albeit in impossibly slow motion, a piece of a planet literally evaporating into space, molecules at a time, carving new patterns into ancient rock. The magnetic mystery deepens. Crustal anomalies and ancient fields. We've talked about Mercury's global magnetic field, that weak but persistent dynamo operating in its liquid outer core. But Mercury has another magnetic story to tell, one written in the rocks of its ancient crust. When MESSENGER flew low over certain regions of Mercury, mapping the planet's magnetic field in detail, it detected local magnetic anomalies, patches where the magnetic field strength was noticeably higher than the surrounding areas. These anomalies are small, localized, and don't appear to be connected to the global dipole field generated by the core. They're crustal magnetic anomalies, places where rocks near the surface have been permanently magnetized, retaining a memory of ancient magnetic fields that no longer exist at the same intensity or configuration. This is seen on other planets too, particularly Mars and the Moon. In both cases, crustal magnetic anomalies tell us that those worlds once had strong magnetic fields billions of years ago, fields generated by active dynamos in their cores, but that those dynamos have since shut down. The ancient field magnetized certain rocks, particularly iron-bearing minerals, aligning their magnetic domains like tiny compass needles. And even after the global field vanished, those rocks retained their magnetization, creating local magnetic signatures that spacecraft can detect billions of years later. Mercury's crustal anomalies might be telling a similar story, Perhaps Mercury's magnetic field was much stronger in the ancient past, when the core was hotter and convection was more vigorous. That stronger field magnetized rocks in certain regions, particularly areas with lots of iron-bearing minerals. Then, as Mercury's core cooled and the dynamo weakened, the global field diminished to its current weak state. But the crustal magnetization remained, preserving a memory of that stronger ancient field. Alternatively, the anomalies might be associated with impact events. Large impacts can generate intense, localized magnetic fields through several mechanisms: plasma produced by the vaporized impactor, shock-induced changes in mineral structure, or interactions between the impact and Mercury's existing magnetic field. These impact-generated fields could magnetize rocks at the impact site, creating anomalies that outlast the impact itself. Messenger's data wasn't quite detailed enough to definitively distinguish between these scenarios, but the presence of crustal magnetic anomalies on Mercury adds another layer to the planet's magnetic story. It suggests that Mercury's magnetic field, already surprising for existing at all on such a small planet, has also evolved over time, possibly changing in strength or configuration as the interior cooled and the dynamo adjusted to changing thermal conditions. Future missions to Mercury, particularly Bepi-Colombo, a joint European-Japanese spacecraft that's currently on its way to Mercury and will arrive in the mid-2020s, will map Mercury's magnetic field with even greater precision. Bepi-Colombo will fly lower, carry more sensitive instruments, and spend more time studying the magnetic environment. It will hopefully answer questions about both the crustal anomalies and the details of how the core dynamo operates, giving us a more complete picture of Mercury's magnetic personality. The long, slow sunset of Mercury's geological life. We've mentioned that Mercury's volcanism ended billions of years ago, that the planet cooled and the mantle solidified and lava stopped flowing onto the surface. But that process didn't happen all at once. It was gradual, a slow fade-out over hundreds of millions or possibly billions of years, not a sudden shutdown. The evidence for this gradual decline is written in the different ages of volcanic plains across Mercury's surface. By counting impact craters on different volcanic deposits and using statistical methods to estimate ages, scientists can construct a rough chronology of Mercury's volcanic activity. The oldest volcanic plains, those first-generation flood basalts, probably erupted somewhere around 3.8 to 4 billion years ago, overlapping with the late stages of the heavy bombardment. These were large-volume effusive eruptions, huge quantities of lava flooding across the landscape and filling in low-lying areas. Younger volcanic deposits, covering smaller areas and with fewer large craters, date to perhaps 3.5 to 3.7 billion years ago. The eruptions were becoming less frequent, less voluminous, as the mantle's ability to generate melt declined. And then, gradually, the eruptions became rarer and rarer. By about 3 billion years ago, or perhaps as recently as 2.5 billion years ago, volcanic activity had essentially ceased entirely. The lithosphere, that rigid outer shell of solid rock, had thickened to the point where magma could no longer break through. The mantle had cooled enough that large-scale melting was no longer possible. Since then, for 2 to 3 billion years, Mercury has been volcanically dormant, silent. The volcanic vents have gone cold. The lava flows have frozen into solid rock. The processes that once resurfaced huge fractions of the planet have shut down permanently. And in that silence, the only significant geological process remaining has been impact cratering. Asteroids and comets continue to hit Mercury, excavating new craters, erasing old features, slowly churning the upper few meters of the crust over time through a process called impact gardening. But there's no internal activity to counterbalance that external bombardment. No volcanism to repave the surface, no tectonics to recycle material. just accumulation of impact scars and the slow, patient modification of those scars by subsequent impacts. It's a quiet fate, perhaps a melancholy one if you anthropomorphize planets, which I admit I sometimes do. Mercury was once active, once dynamic, once capable of reshaping itself from within, and now it's not. It's geologically frozen, locked in a state where change comes only from external forces, not internal vitality. But perhaps there's beauty in that too. Mercury has achieved a kind of geological equilibrium, a steady state where it's no longer fighting against itself, no longer tearing itself apart or building itself back up. It's settled, it's resting, it's allowed itself to simply exist, preserving its ancient features for billions of years, maintaining a surface that's both a history book and a monument. And deep inside, that liquid core still churns, that magnetic heartbeat still pulses, even if the mantle above it has gone silent. Mercury isn't completely dead. It's just moved into a different phase of planetary life, one characterized more by preservation than by activity, more by memory than by change. What a strange journey to Hell's freezer. Let's return one more time to Mercury's polar ice, because the process of how that ice accumulates and stays stable is so beautifully intricate that it deserves a deeper look. Picture a comet impact on Mercury's day side, near the equator, where the surface is blazingly hot. The comet, a mix of ice and rock and organic material, is traveling at maybe 50 kilometers per second. It slams into the surface with unimaginable violence. In the first fraction of a second, the kinetic energy of the impact converts to heat and mechanical energy. The comet vaporizes. The surface rock beneath it melts and vaporizes. A fireball of superheated plasma expands outward. An explosion comparable to millions of nuclear bombs excavates a crater. Most of the water that was in the comet is now water vapor, hot gas expanding rapidly into Mercury's thin exosphere. Individual water molecules, each made of one oxygen atom bonded to two hydrogen atoms, scatter in all directions. Now those water molecules are on their own, bouncing across Mercury's surface in long, graceful parabolic arcs. With each bounce, each hop, there's a chance the molecule will gain enough energy to escape Mercury's gravity entirely. Maybe it absorbs a photon of sunlight and gains enough velocity to break free. Maybe it gets hit by a particle from the solar wind and gets kicked into space. Most molecules delivered by the impact are lost this way within days or weeks. But statistically, just by the randomness of billions of molecules all bouncing in different directions, a small fraction will by chance make a hop that carries them toward the poles, and an even smaller fraction will happen to land in a permanently shadowed crater, one of those deep cold traps where the sun never shines. When a water molecule lands in one of those shadows, the cold grabs it instantly. At 40 or 50 Kelvin, which is typical for the coldest parts of these craters, water ice is stable for billions of years. The molecule doesn't have enough thermal energy to escape. It's frozen to the surface on contact. Over time, layer upon layer, molecule by molecule, impact after impact, over billions of years, the ice accumulates. One molecule here, a dozen there, thousands in one lucky impact, millions in a particularly large comet strike. It all adds up. And once it's there, once it's in the shadow, it stays. Mercury's lack of atmosphere means there's no wind to transport heat into the shadows. The only way heat can reach those permanently shadowed regions is through conduction through the rock itself or through infrared radiation from surrounding sunlit areas, and both of those processes are slow and inefficient. The ice deposits themselves, once they're thick enough, become self-insulating. Ice is a poor conductor of heat. A layer of ice shields the deeper ice beneath it, maintaining even colder temperatures at depth. Computer models suggest that in some of Mercury's deepest cold traps, ice could be stable at depths down to meters, or possibly even tens of meters below the surface. These could be genuine glaciers, admittedly small ones, but thick deposits of water ice that would require considerable energy to excavate and melt. And here's a wonderful detail. The ice deposits probably have layers, like tree rings, recording changes in the rate of comet and asteroid impacts over billions of years. Upper layers might be relatively young, deposited by recent impacts. Deeper layers could be ancient, dating back billions of years to the late heavy bombardment when impact rates were much higher. If we could somehow drill a core through one of these ice deposits and analyze it layer by layer, we'd be reading a history of the inner solar system's bombardment record, preserved in water ice on the hottest planet in the solar system. Each layer would tell us about the impact flux during that era, about the composition of impactors, about how the comet population in the inner solar system has changed over geological time. It's one of the most delightful ironies in planetary science. Some of the best preserved ice deposits in the inner solar system, the most pristine records of ancient water delivery, are sitting on Mercury, literally the last place you'd think to look. Mercury's seasons that aren't quite seasons. We mentioned earlier that Mercury's axis is nearly perpendicular to its orbit, meaning it doesn't have seasons the way Earth does. But that's not quite the whole story, because Mercury's orbit itself is so elliptical that the planet experiences something like seasonal variations, not from axial tilt but from orbital distance. At perihelion, when Mercury is closest to the Sun, the planet is about 46 million kilometers away. At aphelion, when it's farthest, the distance increases to about 70 million kilometers. That's a huge difference, roughly 50% variation in distance. Because the intensity of sunlight follows an inverse square law, falling off with the square of the distance, that orbital variation translates to significant differences in how much solar energy Mercury receives. At perihelion, Mercury receives about 2.3 times more solar energy per square meter than it does at aphelion. For a planet with an atmosphere, this difference would be moderated and spread out by atmospheric circulation, but Mercury has no atmosphere. Each point on the surface responds directly to the changing intensity of sunlight as Mercury moves along its elliptical orbit. So there is a kind of summer and winter on Mercury, not tied to hemisphere or latitude like Earth's seasons, but tied to orbital position and experienced by the whole planet simultaneously. When Mercury is at perihelion, the entire planet is in its hottest season, receiving maximum solar energy. When it's at aphelion, things are relatively cooler, though still incredibly hot by any reasonable standard. Because of Mercury's 3-2 spin-orbit resonance, certain longitudes on Mercury's surface always face the Sun when the planet is at perihelion. These are called the hot poles, and they experience even more extreme heating than other parts of Mercury because they get maximum solar energy when the Sun is at its closest and largest. Other longitudes face the Sun when Mercury is at aphelion. These are the warm poles, which sounds like a contradiction, but is accurate in relative terms. They get their peak heating when the Sun is farther away, so their maximum temperatures are somewhat lower than the hot poles experience. It's a subtle but real variation in Mercury's thermal environment, a consequence of orbital mechanics combining with rotational dynamics to create different thermal zones across the planet's surface. And there's one more seasonal effect worth mentioning. The Sun's apparent size in Mercury's sky changes dramatically throughout the orbit. At perihelion, the Sun appears enormous, about 1.4 times larger in angular diameter than it does at aphelion. If you could somehow safely observe the Sun from Mercury's surface, you'd watch it grow and shrink over the course of each 88-day year, swelling to its maximum threatening size when Mercury swoops closest, then shrinking again as the planet moves away. Combined with the retrograde loop phenomenon we discussed earlier, where the sun sometimes moves backward in the sky. Mercury's solar motion is genuinely bizarre. The sun doesn't just rise, arc smoothly overhead and set like it does on Earth. It rises slowly, takes weeks or months to reach its peak, sometimes hesitates and reverses, then eventually continues on to an equally slow sunset, all while changing size throughout the long day. It's a sky that would look alien, even if you ignored everything else. The blackness, the stars visible at noon, the lack of blue, those are one thing, but the sun itself behaving in such strange ways, looping and growing and shrinking, would be genuinely disorienting. Time would feel different on Mercury, not just because the days are long, but because the most reliable clock we have, the sun's motion across the sky, doesn't behave in a predictable, uniform way. It speeds up and slows down. It reverses. It pulses in size. It's a surrealist sundial, a Salvador Dali painting made real. The upcoming mission, Beeper Colombo's 7-year journey. Mercury has been visited by only 2 spacecraft in history, Mariner 10, which made 3 flybys in 1974 and 1975, and Messenger, which orbited from 2011 to 2015. That's it. In the more than 60 years of space exploration, we've sent dozens of missions to Mars, multiple missions to Venus, countless missions to the Moon, and probes to every planet in the solar system and beyond. But Mercury has had only 2 dedicated visitors. Why so few? Because Mercury is genuinely difficult to reach. Counterintuitively, it takes more energy to send a spacecraft to Mercury than to send one to Mars or even Jupiter. The reason is that to reach Mercury, you have to cancel out a huge amount of orbital velocity. Earth is moving around the Sun at 30 kilometers per second. Mercury orbits much closer to the Sun where orbital speeds are faster, but to get there from Earth, you can't just point toward the Sun and fire your rockets. You have to carefully shed velocity, letting the spacecraft fall inward toward the Sun in a controlled way, making multiple gravitational assists from Venus and Mercury itself to gradually lower your orbit. It's a slow, patient process requiring years of trajectory planning and execution. Messenger took over 6 years to reach Mercury orbit after launch, performing 1 Earth flyby, 2 Venus flybys, and 3 Mercury flybys, before finally having slowed down enough to enter orbit. That's an incredibly complex trajectory, and it required phenomenal precision in navigation and timing. The spacecraft currently on its way to Mercury, Bepi Colombo, is following an even more complex path. Launched in October 2018, it won't arrive at Mercury until late 2025, taking 7 years to complete its journey. Along the way, it's performing 1 Earth flyby, 2 Venus flybys, and 6 Mercury flybys, each one carefully designed to steal a bit more velocity and lower its orbit incrementally. Why such a complicated route? Why not just use more rocket fuel and go straight there? The problem is the tyranny of the rocket equation. The more fuel you carry, the more mass you have, which means you need even more fuel to accelerate that mass, which increases your mass further, requiring even more fuel. It spirals out of control quickly. To carry enough fuel to fly straight to Mercury and slow down into orbit would require such an enormous rocket that the mission would be prohibitively expensive and probably technically impossible with current technology. So, instead, mission planners use gravity assists, stealing tiny amounts of orbital energy from planets to gradually change the spacecraft's trajectory. It takes much longer, but it's feasible with existing rockets and budgets. Bepi Colombo is actually 2 spacecraft in one, a European orbiter called the Mercury Planetary Orbiter, MPO, and a Japanese orbiter called the Mercury Magnetospheric Orbiter, MMO. They're traveling together, stacked on top of each other, with a transfer module providing propulsion, and they'll separate once they reach Mercury, entering different orbits optimized for their different scientific goals. MPO will focus on studying Mercury's surface, interior, and composition. It carries cameras, spectrometers, a laser altimeter, and other instruments designed to build on Messenger's discoveries and answer unresolved questions. Where did Mercury's volatiles come from? How extensive are the polar ice deposits? What minerals are responsible for hollows? How has the surface evolved over time? MMO will study Mercury's magnetosphere, that weak but fascinating magnetic bubble generated by the core dynamo. It will measure how the solar wind interacts with Mercury's magnetic field, how that field varies over time, and what that tells us about the dynamo process operating deep in the core. Together, these two spacecraft will provide the most comprehensive view of Mercury we've ever had, monitoring the planet from multiple perspectives simultaneously, watching how different aspects of Mercury's environment interact and change. It's a mission decades in the planning, years in the traveling, and it represents humanity's continuing commitment to exploring even the most difficult-to-reach corners of our solar system. Mercury may be small, may be overlooked, may be harsh and unforgiving, but it has stories to tell, secrets to reveal, and we're willing to spend billions of dollars and years of effort to hear those stories. That's the beautiful thing about science. Difficulty doesn't make something less worth doing. Mystery makes it more worth doing. Mercury's challenges, its remoteness, its harshness, those things don't diminish its value as a target for exploration. They enhance it. Looking forward, Mercury's lessons for exoplanet science. As we wrap up this long journey through Mercury's paradoxes and peculiarities, it's worth stepping back and asking, why does Mercury matter beyond its own intrinsic interest? What can this small, strange, metal-rich planet teach us that's relevant to the broader universe? The answer is exoplanets. In the past 3 decades, astronomers have discovered thousands of planets orbiting other stars, and many of them are genuinely bizarre by solar system standards. Hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun, super-Earths, rocky planets several times Earth's mass with no analogue in our system, mini-Neptunes, worlds intermediate between Earth and Neptune, ice giants sitting where rocky planets should be, rocky planets sitting where gas giants should be. The diversity of exoplanets has shattered our simple models of planetary formation and taught us that planetary systems are far more varied than we ever imagined, based solely on our own solar system. But here's the thing, Mercury is teaching us the same lesson, just on a smaller scale. Mercury is proof that even within our own solar system, even among planets that formed from the same disk of material around the same star, you can get wild variations, unusual outcomes, planets that don't fit the mold. Mercury's metal-rich composition might have analogues around other stars. Perhaps there are exoplanets out there that are even more metal-rich, giant iron cores with barely any rock at all, formed through even more extreme giant impacts, or even more pronounced compositional gradients in their protoplanetary disks. Mercury's 3-2 spin-orbit resonance is teaching us about tidal interactions and how rotation evolves over time. Many exoplanets are tidally locked to their stars, showing the same face perpetually, and understanding Mercury's evolution helps us understand how those exoplanets reached their current states. Mercury's magnetic field, generated despite the planet's small size, is teaching us that dynamos can persist under a wider range of conditions than we thought. That has implications for which exoplanets might have magnetic fields, which affects their atmospheric evolution and possibly their habitability. Mercury's extreme temperature variations, its lack of atmosphere despite being relatively massive, its ice in permanent shadow, all of these features are teaching us about the range of conditions that can exist on rocky planets, and how local geometry and environmental factors can create niches wildly different from average conditions. In short, every weird feature of Mercury, every paradox and anomaly, is expanding our understanding of what's possible in planetary science. And that expanded understanding helps us interpret the strange and varied worlds we're discovering around other stars. Mercury is a laboratory for extreme planetary science, a test case for processes and conditions that might be even more extreme elsewhere. It's a reminder that planets are individuals, not just average statistics, and that understanding planetary diversity requires studying the outliers as much as the typical examples. And on a deeper level, Mercury is teaching us humility. For decades, scientists thought they understood this planet. It was simple, boring, just a dead moon, orbiting the sun instead of a planet. Crater, 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 nothing interesting. Then we looked closer, and every assumption turned out to be wrong. Mercury had a magnetic field when it shouldn't. It had volcanism when it shouldn't. It had ice when it couldn't. It had shrunk more than predictions suggested. Its composition was more extreme than models predicted. Its rotation was locked in a resonance nobody anticipated before discovering it. Every time we study Mercury in more detail, it surprises us, and that's a powerful lesson for how we approach the rest of the universe. Assumptions are dangerous. Conventional wisdom is often wrong. The truth is usually more interesting, more complex and more wonderful than our simple models suggest. We should expect to be surprised, not just occasionally, but regularly. We should look for the unexpected, embrace the paradoxes, delight in the anomalies, because that's where the real science happens, where genuine discovery occurs, where our understanding grows. Mercury embodies that spirit of surprise. It's the planet that breaks rules, challenges assumptions, and rewards careful observation with revelations that change how we see the entire solar system. The final paradox: beauty and harshness. There's one last thing worth saying about Mercury, something a bit more philosophical and perhaps a bit more personal. Mercury is, by any objective measure, one of the most hostile environments in the solar system for anything we'd recognize as life. It's blasted by radiation. It bakes and freezes through temperature swings of 600 degrees. It has no air, no water on the surface, no protection from meteorites or solar storms. It's been battered, melted, frozen, compressed and irradiated for 4.5 billion years. And yet, there's beauty there, real beauty. The sweeping curves of its lobate scarps, those enormous cliffs casting dramatic shadows across ancient plains, the geometric precision of impact craters, circles within circles, rays radiating across hemispheres, patterns written in stone, the bright hollows scattered like constellations across darker terrain, each one a tiny patch of geological youth. The contrast between heavily cratered highlands and smooth volcanic plains, the boundary between past and present written clearly across the landscape, the stark play of light and shadow in the airless environment, where black is truly black and bright is blindingly bright, with no atmosphere to soften the transition. There's beauty in the orbital mechanics, in that elegant 3-2 resonance that makes Mercury dance with the sun in a way no other planet does. There's beauty in the magnetic field, that stubborn heartbeat that refuses to stop. There's beauty in the ice hiding in shadows, water persisting where it has no right to exist. There's beauty in the geology, in those wrinkle ridges and scarps that tell stories billions of years old. And there's beauty in the paradox itself, in the fact that this small, harsh, extreme world is so much more complex and interesting than it appears at first glance. Beauty doesn't require comfort or familiarity. Beauty can exist in the alien, the hostile, the extreme. Sometimes the most beautiful things are the ones that challenge us, that defy our expectations, that force us to look more carefully and think more deeply. Mercury is beautiful because it's strange. It's beautiful because it surprises. It's beautiful because it exists at all, because it survived the chaos of planetary formation, because it's maintained its geological dignity for 4.5 billion years, despite every force in the universe trying to tear it apart or melt it down or freeze it solid or strip it away. When you look at images of Mercury, really look at them, not just glancing but studying, you start to see that beauty emerge, the subtle color variations that indicate different rock types, the elegant curves of impact ejecta frozen mid-flight by instant solidification, the geometric perfection of crater rims, the flowing textures of ancient lava now frozen in stone, the delicate bright rays that radiate from recent impacts like cosmic artwork. Mercury rewards patient observation. It reveals its secrets slowly, carefully, to those willing to look past the initial impression of just another cratered rock and see the individual character, the unique personality, the specific history written in every feature. And perhaps that's the deepest lesson Mercury teaches, that understanding requires patience, that beauty exists in unexpected places, and that every world, no matter how small or harsh or overlooked, has its own story worth telling. The physics of falling into the sun, but not quite. Let's take a moment to appreciate just how remarkable Mercury's orbit is from a pure physics perspective, because Mercury is performing a gravitational balancing act that's genuinely impressive. Mercury orbits the Sun at an average distance of only 57.9 million kilometers. For comparison, Earth orbits at 150 million kilometers. Mercury is less than 40% of Earth's distance from the Sun. It's hugging close to our star in a way that puts enormous gravitational stress on its orbit. To maintain a stable orbit that close to such a massive object requires tremendous orbital velocity. Mercury whips around the Sun at an average speed of about 47 kilometers per second, making it the fastest planet in the solar system. That's about 170,000 kilometers per hour, fast enough to circle Earth's equator in less than 15 minutes. That speed is necessary because of orbital mechanics. The closer you are to a massive object, the faster you have to move to maintain a stable orbit, and not simply fall inward. Too slow and gravity wins, pulling you down. Too fast and you escape into a higher orbit, or out of the system entirely. Mercury is threading the needle, moving at exactly the right speed to maintain its orbit, month after month, year after year, millennium after millennium. But Mercury's orbit isn't circular, it's noticeably elliptical, with that eccentricity of 0.206 we mentioned earlier. That means Mercury doesn't maintain constant distance or constant speed. At perihelion, racing closest to the Sun, Mercury reaches speeds of about 59 kilometers per second. At aphelion, farther out and moving more leisurely, its speed drops to about 39 kilometers per second. That's a speed variation of 20 kilometers per second, about 72,000 kilometers per hour, over the course of a single orbit. Mercury speeds up and slows down dramatically as it swoops in close and then swings back out, like a gravitational pendulum oscillating between extreme states. From the perspective of celestial mechanics, Mercury is constantly falling toward the Sun and constantly missing, over and over, in an endless dance that's been going on for billions of years and will continue for billions more. Every orbit is a successful miss, a calculated fall that curves into a swing that carries Mercury back around for another attempt. And the Sun's gravity is relentless, always pulling, always trying to drag Mercury inward. Only Mercury's tremendous orbital velocity keeps it aloft, keeps it falling around the Sun rather than into it. If Mercury's velocity suddenly dropped by just a few kilometers per second, the delicate balance would break. Mercury would spiral inward over multiple orbits, eventually falling into the Sun in a final spectacular impact. But that won't happen, at least not on any timescale relevant to human civilization or even human evolution. Mercury's orbit is stable over millions and billions of years. It's been orbiting reliably since the solar system formed, and it will continue orbiting reliably until something dramatic happens to disrupt it. What could disrupt it? Over extremely long time scales, billions of years into the future, orbital resonances with other planets can slowly change Mercury's orbit. Computer simulations that run the solar system forward billions of years sometimes show Mercury's orbit becoming more eccentric, more elongated, until eventually it either collides with Venus, gets ejected from the solar system entirely, or plunges into the Sun. But these outcomes are statistical, not certain, and they play out over timescales of 4 to 5 billion years in the future. For the entire remaining main sequence lifetime of the Sun, Mercury will almost certainly continue its faithful orbit, the innermost sentinel, the closest planetary companion our star has. There's something almost poetic about that faithful service. Mercury has been orbiting the Sun since before Earth had a solid crust, since before life emerged anywhere in the solar system, since before the Moon formed. It has witnessed the entire history of our planetary family, seen every major event, every collision, every epoch of heavy bombardment, every evolutionary change in the Sun itself as it slowly brightens over geological time. Mercury was there at the beginning, and barring catastrophic intervention, it will be there near the end, still orbiting, still falling and missing, still dancing with the Sun in that elegant 3-2 resonance, still maintaining its magnetic field, still accumulating ice in its polar shadows, still being Mercury. The role of Mercury in testing Einstein's relativity. Here's something you might not expect in a discussion about Mercury. This little planet played a starring role in one of the most important confirmations of Einstein's theory of general relativity, the revolutionary framework that describes gravity not as a force, but as a curvature of space-time itself. The story begins in the 19th century, long before Einstein, when astronomers were making increasingly precise measurements of planetary orbits. They noticed something strange about Mercury. Its orbit wasn't quite behaving according to Newton's laws of motion and gravity, laws that had worked perfectly for predicting every other planetary motion in the solar system. Specifically, Mercury's perihelion, the point in its orbit where it comes closest to the Sun, was slowly rotating. This rotation, called perihelion precession, means that each time Mercury completes an orbit, its perihelion is in a slightly different position than it was the previous orbit. Over time, the entire orbit rotates, tracing out a rosette pattern rather than a perfect closed ellipse. Perihelion precession isn't unusual by itself. All planets experience it to some degree, because they're being gravitationally tugged by other planets, which causes small perturbations in their orbits. Astronomers could calculate exactly how much precession each planet should experience based on the known masses and orbits of all the other planets, using Newton's laws. For every planet except Mercury, the calculations matched observations perfectly, but Mercury was precessing too fast. The observed precession rate was about 574 arcseconds per century. The precession that could be explained by other planets' gravitational tugs was only about 531 arcseconds per century. There was an unexplained excess of about 43 arcseconds per century. That might not sound like much. An arcsecond is 1/3600th of a degree. 43 arcseconds is about 0.012 degrees. But astronomical measurements were precise enough to detect this discrepancy clearly, and it was genuinely puzzling. Some astronomers proposed that there might be an undiscovered planet even closer to the Sun than Mercury, a planet they called Vulcan, whose gravitational pull could account for the excess precession. Searches were conducted. Some observers even claimed to have spotted Vulcan transiting across the Sun's face, but none of these observations could be confirmed, and Vulcan remained frustratingly elusive. The mystery of Mercury's orbit remained unsolved for decades, a small but persistent problem that didn't fit into the otherwise beautifully successful Newtonian framework. Then in 1915, Albert Einstein published his general theory of relativity, and one of the very first things he did with his new theory was calculate Mercury's perihelion precession. General relativity predicts that objects moving in strong gravitational fields, particularly those moving at high speeds, should experience effects that Newtonian gravity doesn't account for. The curvature of space-time near a massive object like the Sun is more pronounced than Newton's simpler model suggests, and that extra curvature affects orbits. When Einstein worked through the mathematics of general relativity applied to Mercury's orbit, he calculated an excess precession of almost exactly 43 arcseconds per century. The prediction matched the observations perfectly, with no need to invoke any mysterious undiscovered planet. Einstein was reportedly so thrilled by this result that he experienced heart palpitations. For days afterward, he was excited and energized by the realization that his theory had explained a decades-old mystery that had resisted all other attempts at solution. It was one of the first major confirmations that general relativity was not just mathematically interesting but physically correct, a true description of how gravity actually works in the universe. Mercury, simply by being where it is and orbiting how it does, served as a perfect natural laboratory for testing relativistic effects. It's close enough to the Sun that space-time curvature is strong, it's moving fast enough that relativistic effects are measurable, and its orbit is well characterized enough that precise measurements can detect subtle deviations from Newtonian predictions. Even today, more than a century later, Mercury continues to serve as a testbed for gravitational theories. Messenger's precise tracking of Mercury's orbit, combined with increasingly accurate measurements of the Sun's mass distribution and the gravitational effects of other planets, has allowed scientists to test general relativity to even higher precision. So far, Einstein's theory continues to pass every test. Mercury's perihelion precession remains perfectly consistent with general relativity's predictions. Alternative theories of gravity that predict slightly different precession rates have been ruled out by observations. Mercury, that small, hot, overlooked planet, helped prove one of the most profound and revolutionary ideas in the history of physics. Every time it completes an orbit, it's performing a relativistic experiment, demonstrating the curvature of space-time, confirming Einstein's insights. And it does this unconsciously, automatically, simply by existing and following the geodesics, the natural paths through the curved space-time created by the Sun's mass. There's something wonderful about that. Mercury isn't trying to teach us physics. It's just being Mercury. But by observing it carefully, by measuring its motion precisely, by taking it seriously as an object worthy of detailed study, we've learned fundamental truths about the nature of space, time, and gravity itself. That's the power of careful observation and the value of studying every world in our solar system, even the small ones, even the seemingly simple ones. Each planet is performing countless natural experiments, demonstrating physical principles, offering clues about how the universe works. We just have to watch, measure, and think deeply about what we're seeing. The Messenger mission, 4 years of revelation. It's worth spending some time appreciating just how much the Messenger mission transformed our understanding of Mercury, because the difference between pre-Messenger and post-Messenger Mercury is like the difference between a blurry photograph and an IMAX movie. Messenger launched in August 2004 and finally entered orbit around Mercury in March 2011. After that long, complex journey involving multiple gravitational assists, once in orbit, it began systematically mapping the planet in unprecedented detail. Previous to Messenger, our knowledge of Mercury came primarily from Mariner 10's 3 brief flybys in 1974 to 1974 to 1975. Mariner 10 had imaged about 45% of Mercury's surface, leaving more than half the planet completely unseen by any spacecraft. The images that existed were low resolution by modern standards, and the measurements of Mercury's composition, magnetic field, and other properties were limited to what could be gathered during brief encounters lasting hours. MESSENGER changed everything. Over 4 years in orbit, from 2011 to 2015, it mapped 100% of Mercury's surface in high resolution, not just once but multiple times, under different lighting conditions from different angles, allowing for detailed topographic mapping and photographic coverage that revealed features as small as a few meters across in the best images. The spacecraft carried 7 scientific instruments, each designed to answer specific questions about Mercury. A dual imaging system with wide-angle and narrow-angle cameras captured more than 250,000 images of Mercury's surface, documenting every crater, every scarp, every volcanic plain, every unusual feature. A laser altimeter measured surface elevations with precision, creating detailed topographic maps that showed exactly how high mountains rose and how deep craters descended. A magnetometer measured Mercury's magnetic field from orbit, mapping its structure and monitoring how it varied over time. 2 spectrometers analyzed the composition of surface materials by measuring which wavelengths of light and gamma rays the surface emitted and reflected. A neutron spectrometer searched for hydrogen concentrations that would indicate water ice, and instruments to measure the charged particles and plasma environment around Mercury documented how the solar wind interacted with Mercury's magnetosphere. All of these instruments working together produced a comprehensive portrait of Mercury that was unimaginably better than anything we had before. It was like going from knowing Mercury as a distant acquaintance you'd met briefly a few times, to living with Mercury for 4 years, observing it day and night, in all moods and conditions, learning its personality in intimate detail. Many of the discoveries we've discussed in this script came directly from MESSENGER data. The confirmation of water ice at the poles, identified through neutron spectrometer measurements and imaging of permanently shadowed craters, the discovery of hollows, those strange bright depressions that appeared to be actively forming, the detailed mapping of volcanic plains, and the evidence for explosive volcanism, the measurements of Mercury's unusually high sulfur content and volatile abundances, the discovery of the weird terrain, antipodal to Caloris, and the understanding of its formation, the precise mapping of lobate scarps, and the calculation of Mercury's total shrinkage, the detailed characterization of Mercury's offset magnetic field and its asymmetry. None of this would have been possible without MESSENGER spending years in orbit, patiently collecting data, building up comprehensive data sets that scientists could analyze in depth. One-time flybys simply can't gather that kind of detailed, systematic information, and MESSENGER operated in an incredibly harsh environment. Mercury's proximity to the Sun meant the spacecraft was constantly bathed in intense solar radiation and heat. Engineers had to design elaborate sunshades and cooling systems to protect the sensitive instruments. They had to carefully plan observations to avoid pointing cameras directly at the Sun. They had to manage limited fuel resources, because Mercury's lack of atmosphere meant no aerobraking was possible, so every orbital adjustment required precious rocket fuel. The mission was extended twice beyond its original 1-year timeline, as instruments continued functioning and returning valuable data. Eventually, in April 2015, MESSENGER ran out of fuel. With no way to maintain its orbit, the spacecraft gradually descended and finally impacted Mercury's surface at high speed, creating a new crater about 16 meters across somewhere in the northern hemisphere. It was a fitting end, in a way. MESSENGER became part of the world it had studied, adding its own small mark to Mercury's surface, a crater that future missions might someday image and identify. The spacecraft's impact crater is a monument to human curiosity, to our drive to explore and understand even the most difficult-to-reach places in our cosmic neighborhood. The scientific papers resulting from MESSENGER data number in the hundreds, and scientists are still analyzing the data, still making new discoveries from images and measurements collected years ago. Some questions require comparing different types of data, correlating observations from different instruments, building models that match all the constraints. But work continues even though the mission ended nearly a decade ago. That's the legacy of a successful planetary mission. It's not just the discoveries announced during the active phase, it's the data sets that remain valuable for decades. The measurements that future scientists will return to again and again, the complete portrait of a world that serves as a reference and a foundation for all future studies. Messenger gave us Mercury as a known world, not a mysterious one, and in doing so, it made Mercury more interesting, not less, because every answer revealed new questions, every discovery opened new mysteries, every measurement showed new complexity. The sound of silence, what you'd hear on Mercury. Let's do a thought experiment. Imagine you're standing on Mercury's surface, somehow protected from the extreme temperatures and radiation by an advanced spacesuit. What would you hear? Nothing. Absolute silence. The most complete, total absence of sound you can possibly imagine. On Earth, we're never in true silence. Even in the quietest room, in the deepest cave, far from any human activity, there's always something. The sound of your own breathing, amplified by the confined space. Your heartbeat, transmitted through bone conduction to your ears. The faint whisper of air moving. The occasional creak of rock adjusting to temperature changes. The distant rumble of geological activity. Blood flowing through vessels near your eardrums. Creates subtle sounds we never consciously notice, but which are always there. And of course, on Earth's surface there's always atmospheric sound. Wind, even the gentlest breeze, creates sound as it moves around objects and through spaces. Distant thunder, animals calling, human activity, waves breaking, rain falling. The gentle rustle of leaves, the subtle pressure changes as weather systems move through. Even in a desert far from any life or human presence, the atmosphere itself creates sound through thermal currents and pressure variations. But on Mercury, there is no atmosphere to carry sound waves. Sound is a pressure wave, a mechanical vibration that propagates through matter. It requires a medium, air, water, rock, anything made of atoms that can vibrate and transmit that vibration to neighboring atoms. In the vacuum of Mercury's exosphere, there are so few atoms per cubic meter that sound waves cannot propagate. There's nothing to vibrate, nothing to transmit the vibration. If you were standing on Mercury and a boulder tumbled down a cliff face 10 meters away from you, you would see it falling, see it hit the ground, see dust and fragments scatter from the impact, but you would hear nothing, not even a whisper. The impact would send vibrations through the rock beneath your feet, and those vibrations might reach your boots and transmit through your suit as subtle tactile sensations. But no airborne sound would reach your ears because there's no air to carry it. If another astronaut stood across a crater from you and shouted, you'd see their mouth moving but hear nothing. Radio communication would work fine because radio waves don't need a medium. They propagate through vacuum. But acoustic sound, the compression waves in air that we call speaking or shouting, would not exist. The astronaut's vocal cords would vibrate, but those vibrations would find no air to push, no medium to create pressure waves in, and the sound would die instantly at their lips. A meteorite impact somewhere on the horizon would produce a flash of light as superheated rock and metal vaporized, but no thunder, no boom, no rumble would follow. The light would reach you at the speed of light, about 300,000 kilometers per second. Seismic waves through Mercury's crust would reach you at a few kilometers per second, depending on the rock properties, and you might feel the ground shake. But no acoustic sound would arrive because there's no atmosphere to carry it. Standing on Mercury would be like being deaf, except it's the universe that's mute. not you. Everything happens in perfect, eerie silence. The sun blazes overhead in the black sky, but makes no sound. Your own movements, your footsteps, your interactions with equipment, all silent, except for vibrations transmitted through the surface and through your suit. The only sounds you would hear would be those generated inside your spacesuit, your own breathing, the hum of life support systems, your heartbeat, the occasional click or beep of equipment, and maybe, through radio, the voices of other astronauts. But the external world would be completely, utterly silent. For some people, this might be peaceful, meditative, a kind of sensory simplicity. For others, it might be deeply unsettling, because humans are evolved to rely on sound for awareness of our surroundings. We use hearing to detect danger, to communicate, to orient ourselves in space. An environment where sound doesn't exist would feel fundamentally alien, wrong, incomplete. But it's Mercury's natural state. Silence is what Mercury has experienced for its entire existence. It has never heard the impacts that have scarred its surface. It has never heard the rumble of its own volcanic eruptions, the grinding of its crust as lobate scarps formed, the crash of rocks tumbling down crater walls. All of Mercury's violent, dramatic geological history has unfolded in perfect silence, a movie playing with the sound turned off. There's something profound about that. Mercury's story has been told without words, without sound, purely through visual and tactile changes to its surface and structure. It's a story written in stone and told in silence, patient and eternal. The chemistry of extremes, why Mercury's composition matters for astrobiology. You might think that a discussion of Mercury would have nothing to do with astrobiology, the study of life in the universe. After all, Mercury is almost certainly lifeless, one of the most hostile environments in the solar system, with no liquid water, no organic chemistry on the surface, no temperate conditions anywhere. But Mercury's composition and chemistry actually have important implications for understanding the building blocks of life and where life might arise elsewhere in the universe. Here's why Mercury demonstrates that the inner solar system, particularly the regions very close to stars, can retain and concentrate certain volatile elements that are crucial for life, elements like sulfur, carbon, and even water delivered as ice to the poles. Despite Mercury's proximity to the Sun, despite billions of years of intense solar radiation, these volatiles are still present. This tells us that rocky planets forming in the habitable zones of other stars, regions where liquid water could exist on a planet's surface, will almost certainly have access to the volatile elements needed for life. If even Mercury, at 0.39 AU from the Sun, can retain these elements in some form, then planets at 0.8 to 1.5 AU around Sun-like stars will definitely have them. Mercury also demonstrates the range of planetary compositions that are possible. We know that Earth-like planets with roughly equal proportions of rocky mantle and metallic core can support life, at least one example, anyway. But what about planets with different compositions? Could life emerge on a planet that's more metal-rich than Earth, closer to Mercury's extreme composition? We don't know, but Mercury gives us constraints. A planet needs enough rocky material to form a substantial crust and mantle where complex chemistry can occur. It probably needs tectonic activity, or volcanism, to recycle materials and create chemical disequilibrium, which many scientists think is necessary for life. A planet that's too metal-rich might not have enough rocky mantle to support these processes. On the other hand, a metal-rich planet would have a stronger magnetic field, assuming its core remains liquid, which could provide better protection against cosmic radiation and stellar winds. That protection could be beneficial for surface life or for maintaining an atmosphere. Mercury's sulfur-rich chemistry is also interesting from an astrobiological perspective. On Earth, Many primitive organisms use sulfur compounds in their metabolism. Sulfur-based biochemistry is considered plausible for life in environments where oxygen is scarce. A planet with Mercury-like high sulfur abundances might provide interesting opportunities for sulfur-based life, assuming other conditions like liquid water and moderate temperatures were also present. The discovery of water ice on Mercury, delivered by comets and asteroids and preserved in cold traps, demonstrates a mechanism for water delivery that probably operates around many stars. Comets and asteroids are common byproducts of planetary system formation. They inevitably hit inner planets, delivering water and organic compounds even to worlds that form too hot to retain these materials during their initial accretion. This impact delivery mechanism means that planets don't have to form in the habitable zone to eventually acquire water. They can form elsewhere and receive water later through impacts. This significantly expands the range of potential habitable worlds and suggests that water may be more widely distributed among rocky planets than we might otherwise expect. Mercury is also teaching us about how atmospheres are lost or retained. Its small size and proximity to the Sun resulted in complete atmospheric loss. But where's the boundary? How large does a planet need to be? How far from its star to retain an atmosphere over billions of years? Mercury provides one data point in the parameter space, helping us understand the conditions under which atmospheres are stable. This is directly relevant to assessing the habitability of exoplanets. When we detect a rocky planet around another star, one of the key questions is whether it has an atmosphere. Mercury teaches us that small planets close to their stars are at high risk of atmospheric loss, which would preclude surface liquid water and likely preclude life as we know it. Finally, Mercury's long-term geological evolution, its transition from an active world with volcanism and tectonic activity to a dormant world where only impact processes continue, gives us insight into planetary lifetimes. If life requires geological activity to maintain chemical cycling and environmental conditions, then planets have limited windows of habitability corresponding to their geologically active periods. Mercury's window closed billions of years ago when its volcanism ceased. Earth's window is still open and will remain so for hundreds of millions of years at least. Understanding what controls these windows, what determines how long a planet stays active, is crucial for assessing where and when life might arise in the universe. So Mercury, despite being lifeless and inhospitable, is actually quite informative for astrobiology. It's expanding our understanding of planetary diversity, volatile delivery mechanisms, atmospheric evolution, and the factors that control geological activity. All of these insights feed into our growing understanding of where life might exist beyond Earth. The future of Mercury exploration. What comes next? We've mentioned Bepi Colombo, the joint European-Japanese mission currently on its way to Mercury, due to arrive in late 2025. But what else might the future hold for Mercury exploration? Bepi Colombo will provide our most detailed look at Mercury yet, with 2 spacecraft studying the planet simultaneously from different orbits. The European Mercury Planetary Orbiter will make detailed measurements of the surface, interior, and composition. The Japanese Mercury Magnetospheric Orbiter will study the magnetic field and its interaction with the solar wind in unprecedented detail. Together, they should answer many outstanding questions. How deep are the polar ice deposits, and exactly what are they made of? What minerals are responsible for hollows, and are they actively forming today? How does Mercury's magnetic field vary over time, and what does that tell us about the dynamo process in the core? What's the detailed structure of Mercury's interior, and can we detect any remaining liquid layers besides the core? But Bepi Colombo is an orbital mission. To truly understand Mercury in complete detail, we'll eventually need to land on the surface, deploy instruments that can analyze rocks directly, maybe even return samples to Earth for detailed laboratory analysis. A Mercury lander would face enormous engineering challenges, The extreme daytime temperatures would require sophisticated cooling systems or operations limited to dawn-dusk periods or polar regions. The lack of atmosphere means no parachutes or aerobraking. Braking. Landing would have to be entirely propulsive, requiring significant fuel. The intense solar radiation would quickly degrade electronics and solar panels unless they're specially hardened. But these challenges aren't insurmountable. Engineers have landed spacecraft on Venus, which has its own extreme challenges. They've landed on asteroids and comets. They've operated rovers on Mars for years. With sufficient investment and clever engineering, a Mercury lander is feasible. What might a lander do? It could analyze the composition of different geological units in detail, measuring not just what elements are present but what minerals they're in, providing ground truth for orbital measurements. It could measure heat flow from the interior, constraining models of Mercury's thermal evolution. It could deploy seismometers to listen for Mercury quakes, providing information about internal structure and ongoing contraction. It could sample ice directly from a permanently shadowed crater, analyzing its composition and isotopic ratios to determine where it came from and how old it is. A sample return mission would be even more ambitious, but tremendously valuable, bringing back even a small amount of Mercury rock and ice for laboratory analysis would allow studies that aren't possible with remote sensing. Precise age dating using isotopic measurements. Precise age dating using isotopic measurements. Detailed mineralogy and petrology. Analysis of trace elements and their distributions. Identification of any organic compounds that might have been delivered by impacts and preserved in ice. These kinds of detailed studies have been crucial for understanding the Moon, Mars, and meteorites from asteroids and Mars. They provide a level of information that remote sensing simply can't match, no matter how sophisticated the orbital instruments. Looking further into the future, could humans ever visit Mercury? It's possible, but would require technology and infrastructure significantly beyond what we have today. The journey time is long, the environment is harsh, and there's no atmosphere for aerobraking or in-situ resource utilization of atmospheric gases. But Mercury does have resources that might be valuable. Abundant sunlight for solar power, metals in its crust that could be mined and processed, and water ice at the poles that could provide drinking water, breathable oxygen and rocket fuel through electrolysis. In some far future scenario where the inner solar system is extensively settled and developed, Mercury might play a role, perhaps as a source of raw materials or as a location for solar observation posts taking advantage of the intense sunlight and proximity to the Sun. But realistically, human exploration of Mercury is probably many decades away at minimum, likely longer. The Moon and Mars are far more accessible and forgiving environments for human habitation and will likely be the focus of human space exploration for the foreseeable future. In the meantime, robotic missions will continue to study Mercury, slowly peeling back layers of mystery, answering old questions and raising new ones, building our understanding of this strange little world piece by piece, measurement by measurement, image by image. And that's fine. There's no rush. Mercury has waited billions of years for us to discover its secrets. It can wait a few more decades or centuries for us to fully explore it. The planet isn't going anywhere. It will still be there, faithfully orbiting, patiently preserving its geological record whenever we're ready to visit and learn from it. Mercury in culture, the swift messenger. Before we conclude, it's worth acknowledging Mercury's place in human culture and mythology, because the planet has fascinated humans for thousands of years, long before we understood what planets actually were. To ancient observers, Mercury was one of the wandering stars, an object that moved against the background of fixed stars in complex, unpredictable patterns. Because Mercury orbits so close to the Sun, it's only visible shortly after sunset or shortly before sunrise, appearing for a few weeks, then disappearing in the sun's glare, then reappearing on the other side. The ancient Greeks initially thought these were two different objects: Apollo when it appeared before sunrise, Hermes when it appeared after sunset. Eventually, they realized these were the same object, a single wandering star that alternated between morning and evening appearances, and they named it after Hermes, the messenger god, because of its swift motion across the sky. The Romans later renamed it Mercury, their equivalent of Hermes, and that name has stuck in Western languages. The planet was named for the god's speed, his role as a messenger traveling swiftly between gods and mortals, his wings on his sandals and helmet that granted him the ability to move faster than anyone else. It's an apt name. Mercury is indeed the swiftest planet, completing its orbit faster than any other world in our solar system. If the gods needed a messenger to carry news rapidly throughout the heavens, Mercury would be the right planet for the job. Other cultures had their own names and associations for Mercury. In ancient China, Mercury was called Chenexing, meaning the hour star, referring to its regular appearances at dawn and dusk. In India, it was Buddha, associated with wisdom and communication, again reflecting the messenger communication theme. The Maya, with their sophisticated astronomical observations, tracked Mercury's motions carefully and associated it with war and conflict, perhaps because of its reddish color when viewed low on the horizon through atmospheric haze, though this association was more commonly applied to Mars in other cultures. In medieval European alchemy, Mercury was associated with the metal mercury quicksilver, the only metal that's liquid at room temperature. The connection was symbolic. Both the metal and the planet were seen as quick changeable, hard to pin down. The astrological symbol for both the planet and the metal is the same, the symbol combining elements representing spirit, matter, and the crescent of the soul, or receptivity. In astrology, Mercury is associated with communication, intellect, travel, and commerce. People with strong Mercury influences in their birth charts are supposedly quick-witted, communicative, adaptable, sometimes mercurial, the adjective deriving from the god and planet, meaning changeable or volatile. Whether you put any stock in astrology or not, it's interesting that Mercury's cultural associations emphasize speed, communication, change, and intellect. These qualities, in a metaphorical sense, actually align reasonably well with what we now know about the planet scientifically. Mercury is indeed changeable, experiencing extreme temperature swings and complex orbital dynamics. It is swift, the fastest orbiting planet. It does challenge our intellect, constantly surprising us with discoveries that contradict our assumptions. Mercury has also appeared in science fiction, though less frequently than Mars or Venus. Early science fiction often portrayed Mercury as tidally locked, with one face eternally baking in sunlight and the other frozen in darkness, and stories would be set in the narrow twilight zone between extremes where conditions might be tolerable. This was based on the incorrect pre-1965 assumption about Mercury's rotation. Once the 3-2 resonance was discovered, that science fiction trope became obsolete, and Mercury appeared less frequently in fiction, perhaps because its actual characteristics don't lend themselves to exciting storytelling as easily as Mars's deserts or Venus's clouds or the moons of Jupiter. But Mercury still shows up occasionally, usually as a challenging environment for near-future space exploration stories, a place where survival is difficult and where the extreme conditions create dramatic tension. In our cultural consciousness, Mercury occupies a unique space, the closest planet to the Sun, the fastest in orbit, the smallest of the classical planets, the one that's hardest to see from Earth, requiring patience and careful timing to observe. It's a planet of extremes and superlatives, which gives it a certain cachet even though it's not as immediately accessible or relatable as Mars. And perhaps that's appropriate. Mercury is special precisely because it's extreme, because it occupies a unique niche, because it's not like any other world we know. its cultural identity as the swift messenger, the challenging small planet closest to the Sun, matches its scientific identity reasonably well. Names matter. They shape how we think about things. Mercury's name constantly reminds us of its speed, its proximity to the Sun, its role as the innermost sentinel of our planetary system. Every time we say the planet's name, we're invoking thousands of years of human observation and mythology, connecting our modern scientific understanding to ancient stargazers who watched the same wandering light move across their skies and wondered what it was. The long goodbye, Mercury's eventual fate. All things end eventually, and Mercury is no exception. What does the distant future hold for this small, resilient world? The most immediate consideration is the Sun itself. The Sun is currently a main sequence star, steadily fusing hydrogen into helium in its core, and it's been doing this for about 4.6 billion years. It has another 5 billion years or so of stable hydrogen fusion ahead of it. But stars don't live forever. Eventually, the Sun will exhaust the hydrogen in its core. When that happens, fusion will begin in a shell around the inert helium core, and this will cause the Sun to expand dramatically, becoming a red giant. The Sun will swell to perhaps 100 times its current diameter, engulfing Mercury's current orbit. What will happen to Mercury during this transformation? The timeline is uncertain, but most models suggest Mercury will be vaporized and consumed when the Sun becomes a red giant. The planet will spiral inward through the Sun's expanding outer envelope, experiencing intense drag from the tenuous but still substantial gas. That drag will slow Mercury's orbit, causing it to spiral inward further, accelerating the process. Eventually, Mercury will plunge into the denser inner layers of the red giant Sun and vaporize completely, its atoms mixed into the stellar envelope. It's a dramatic end, a final plunge into the Sun that Mercury has been faithfully orbiting for billions of years. Mercury will become part of the Sun, its materials absorbed back into the star, recycled into the stellar matter that will eventually be ejected into space when the Sun dies. But this fate is billions of years away, about 5 to 7 billion years in the future. Between now and then, Mercury will continue orbiting much as it does today, slowly cooling, slowly accumulating more ice at the poles, slowly gaining new impact craters, but otherwise stable and unchanging. There are other potential fates, though they're less likely. As mentioned earlier, computer simulations of the solar system's long-term orbital evolution sometimes show Mercury's orbit becoming increasingly eccentric over billions of years due to gravitational resonances with Jupiter and Venus. In some simulations, Mercury's orbit becomes so elongated that it eventually crosses Venus's orbit, leading to a possible collision. A Mercury-Venus collision would be spectacular, though of course there would be no one around to witness it, unless future civilizations from elsewhere in the galaxy happen to be observing our solar system. The impact would be violent, possibly destroying both planets, or at least dramatically reshaping them, creating huge amounts of debris that might eventually coalesce into a new, different planet, or into a ring of material around the Sun. Alternatively, in some simulations, Mercury gets ejected from the solar system entirely, flung out into interstellar space by a close gravitational encounter with another planet. Mercury would then wander the galaxy as a rogue planet, a frozen, dark, lonely world traveling through the vast emptiness between stars, slowly cooling to just a few degrees above absolute zero, its surface ice frozen solid even in previously shadowed regions. These scenarios are unlikely, perhaps less than 1% probability according to most simulations, but they're possible over very long timescales. The solar system's orbital dynamics are chaotic in a technical sense, meaning that small initial differences can amplify over time into radically different outcomes. Predicting precisely what will happen billions of years from now is impossible. We can only assess probabilities. But whether Mercury is consumed by the Sun, collides with Venus, gets ejected into interstellar space, or simply continues orbiting stably until the Sun dies and ejects its outer layers, Mercury's ultimate fate is sealed. The planet will not last forever. Nothing does. And yet, for the entire history of life on Earth, from the first simple cells billions of years ago, through the evolution of all the incredible diversity of life we see today, including ourselves, Mercury has been there, orbiting faithfully, serving as the innermost marker of our solar system. It has witnessed all of Earth's story from its cosmic vantage point, silent and patient. Mercury will likely continue witnessing Earth's story for billions of years into the future, watching whatever happens to our planet and to life, still orbiting, still being Mercury, until finally, in the distant twilight of the solar system, its long service ends. There's something moving about that perspective, about seeing Mercury not just as a geological object or a collection of physical properties, but as a companion on our cosmic journey, a fellow traveller through time that's been part of our planetary family since the very beginning, and will remain so until the end. Conclusion: the paradox perfected. So here we are, at the end of our long journey through Mercury's paradoxes and wonders. Let's bring it all together. Mercury is the planet of extremes and contradictions. It's the smallest planet, but has the largest core relative to its size. It's the hottest planet on average, but has ice at its poles. It orbits fastest but rotates slowly. It should be geologically dead, but has an active magnetic field. It formed closest to the Sun, but retained volatiles that should have been lost. It has no atmosphere, but has an exosphere, and even a comet-like tail. It appears simple, but reveals complexity in every measurement. These paradoxes aren't flaws or anomalies. They're essential to what Mercury is. Mercury is defined by its contradictions, characterized by its extremes, made interesting precisely because it doesn't fit our neat categories and simple models. And through all these paradoxes, Mercury teaches us profound lessons about planetary science, about the solar system's formation and evolution, about how wrong our assumptions can be, and how important it is to look closely, measure carefully, and remain open to surprise. Mercury reminds us that every world is an individual with its own story, its own character, its own collection of features and processes and history that make it unique. There are no generic planets, no average worlds. Each one is shaped by particular circumstances, random events, local conditions that will never be exactly replicated anywhere else. Mercury reminds us that understanding requires patience and careful study. Quick glances give misleading impressions. Assumptions lead us astray. Only through sustained observation, multiple types of measurements, creative thinking, and willingness to revise our models do we approach genuine understanding. Mercury reminds us that beauty and interest exist in unexpected places. You don't have to have Earth-like conditions or familiar landscapes to be fascinating. Extreme environments, harsh conditions, alien landscapes can be just as compelling, just as worthy of study and appreciation as more familiar places. Mercury reminds us that size doesn't determine importance. The smallest planet has taught us things that no other world could teach, served as a test bed for general relativity, demonstrated that dynamos can operate in tiny planets, shown us that volatiles can persist in the inner solar system, and generally punched far above its weight class in terms of scientific value. And Mercury reminds us that there's still so much to discover. Even after Messenger's 4 years of intensive study, even with Bepi Colombo on its way to study the planet in even more detail, there are still mysteries. How did Mercury form? Exactly what process or combination of processes gave it its unusual composition? How long will its magnetic field persist? What's the detailed structure of its core and the dynamics of its dynamo? Are hollows actively forming today? What's the complete inventory of volatiles in the polar ice? What other surprises await when we look more closely? These questions will take decades to answer, possibly longer. Some might require landing on the surface, drilling into ice, analyzing rocks directly, deploying long-term monitoring equipment. Some might remain uncertain even then, limited by how much we can reconstruct from incomplete geological records and ambiguous data. But that uncertainty, those unanswered questions, that's what makes Mercury exciting. It's not a solved problem. It's an ongoing investigation, a continuing story, a world that still has secrets to reveal to those patient and curious enough to study it. So, the next time someone mentions Mercury, the next time you see it as a bright star near the horizon at dawn or dusk, the next time you see an image of its cratered surface, remember, you're looking at one of the most paradoxical, most extreme, most surprising, and most scientifically valuable worlds in our solar system. You're looking at a planet that has survived for 4.5 billion years in one of the harshest environments imaginable, that has preserved in its rocks and surface features a record stretching back to the solar system's birth, that continues to operate a magnetic dynamo when it has no right to, that harbours ice on the surface of the hottest planet through sheer geometric luck. You're looking at a world that broke every rule we tried to impose on it, that surprised us repeatedly, that taught us humility and wonder in equal measure. You're looking at Mercury, the paradox planet, the smallest world with the biggest lessons, the swift messenger still faithfully carrying news from the inner solar system to anyone curious enough to listen. And that, my friends, is why Mercury matters, not despite its harshness and extremes, but because of them, not despite being small and overlooked, but because it rewards those who take it seriously, not despite its contradictions, but because those contradictions reveal deeper truths about how planets work, how the solar system formed, and how gloriously complex and surprising the universe really is when you look beyond the surface and into the details. And this has been that story, told as completely as possible in this moment, with the knowledge we have today, knowing that future discoveries will add new chapters, revise old conclusions, and continue Mercury's tradition of surprising us. Mercury is proof that the unexpected is possible, that assumptions should be questioned, that patient observation reveals wonders, and that every world, no matter how small or harsh or distant, has its own story worth telling. Sweet dreams, and may your mind wander through the cold shadows and blazing plains of our solar system's innermost world, marveling at ice existing where it shouldn't, at a magnetic heart that refuses to stop beating, at craters billions of years old and hollows forming today, at a planet that looks simple but reveals itself, slowly and patiently, to be wonderfully, gloriously, paradoxically complex. The story of the little planet that could and did and continues to do so against all reasonable expectations, forever Mercury, forever paradoxical, forever fascinating. Mercury awaits, orbiting faithfully, holding its secrets close, ready to share them with anyone willing to look carefully and think deeply. The paradox planet persists, as it always has, as it always will, until the sun's final transformation billions of years hence. Until then, Mercury keeps spinning in its 3-2 resonance, keeps generating its offset magnetic field, keeps accumulating ice molecule by molecule in its polar shadows, keeps telling its story to anyone listening.